Okay, I'm very happy to welcome all of you to our second day of FRIDA. We'll have 4 more exciting talks today and hopefully lively discussion. We're starting with Jochen Hönicke, who's a senior researcher here in Freiburg. Actually, if we would be there physically, that would be the place. Jochen is very well known for his work on program analysis and verification and on SMT solving and decision procedures for data structures like arrays. And today he's talking about verification of distributed parameterized programs. And I'm excited to hear what you have to say.
Thank you. So I want to show I want to give a compositional proof for the Mach-Shootdown algorithm today. And this is based on our popular paper from 2017. Which is thread modularity on many levels, and it's joint work with Rupert Majumdar and Andreas Podelsky. So let's start with the kind of programs that we want to verify. So we want to verify parametrized programs that are parametrized in the number of threads. So we have program PN, that is the parallel composition of n threads. And each of the n threads executes the same thread template T. And these programs these threads communicate via shared global variables G, and each thread has its own local variables, which are here indicated with xi to indicate that every thread has its own copy. And the kind of properties that we are interested in are safety properties. So we introduce an error condition, and we want to show that the program is free of errors. And the error condition can talk about the global variables and the local variables of, say, 2 threads, x1 and x2. And since the whole program is symmetric, so every thread is basically the same, executes the same thread template. If we show that it's true for x, if an error condition cannot be reached for x1 and x2, then it cannot be reached for any pair of programs, of threads in the program. And what we want to show is, or what our goal is a thread modular proof for the program P that works for any number of threads n. So we don't want to verify it for a fixed number like 3 or 4, but for any number of threads, it should be correct.
Just a question, sorry, maybe I didn't hear very well. So the error condition is only over 2 threads, or?
Yeah, usually it's about 1 or 2 threads. So we basically want to show that every thread cannot violate an assertion, or sometimes we want to show mutual exclusion, and then we have an error condition over 2 threads.
I see.
And by symmetry, it holds for all threads, because every thread template, every thread is basically the same.
Okay, I see.
I also have a question. The shared global variables, is that a fixed number, and is it a finite set of values or infinite?
We don't restrict the thing. So there is a fixed number of global variables.
Okay, but they could be integers.
But they can be integers of arbitrary size.
Okay.
Or they could be more complicated, but then we need more complicated tools to verify.
Okay.
So let's illustrate this concept with a very simple algorithm for mutual exclusion, the ticket algorithm. And you may actually have seen it in some supermarket. For example, in Germany, we have this algorithm implemented sometimes. And it basically consists of 3 parts. So there is a ticket dispenser where you can draw a ticket. And when you draw a ticket, you get a ticket with a ticket number. And then you have a third part, the now serving display, where you can see which ticket is currently served. And if it changes to your number, then you can go wherever you want to go and get served. And this should ensure mutual exclusion if used correctly. And this algorithm can be very easily implemented in this kind of thread templates. So we use two global variables, S and T, and S is basically the number that is displayed on the now serving display, and T is the number that is the next ticket number that is given by the ticket dispenser. And then there's a local variable that is local. Every thread has its own copy of this variable, and this is basically the number on the ticket that the thread has taken. So the threads are the ones that draw the ticket. The initial condition is that S and T is the same number, because otherwise the system wouldn't be safe, or it wouldn't work at all. And we want to show mutual exclusion. So we have a thread template with 3 locations, idle, wait, and critical, and we want to show that no 2 threads are uncritical at the same time. So they all start in the idle state. It's probably missing an init, so init is S equal T, and everyone is idle. And then when they are idle, they can draw a ticket and switch to the wait state. And the ticket drawing is just that they copy the ticket number, the current ticket number, into their local variable M, and atomically also increase the ticket number so that the next thread will get a different ticket number. Then in the wait state, they wait for the serving display to show at least their number. So usually it's equal to M1 when they switch to the critical section, if everything is correct. I put a greater equal here, just so that they don't starve if something goes wrong, but it shouldn't matter. And once they are in the critical section, they get served. And when they are done, they here the threads increase the number on the display by 1. And this way, the next thread can enter the critical section. So this is the kind of program that we want to prove, and we want to prove that no 2 threads are in critical section, or we want to prove that the first and the second one are not in the critical section, and then by symmetry we know it for all threads. And we want to do a thread modular proof. This is what we really would like to have, that we write an invariant to every location of one of the threads. And since they are all equivalent by symmetry, we can use the same invariants for each thread. So we just consider the first thread here. And for every location, we write an invariant that should hold while the thread is in this location. And then we need to prove inductivity, that whenever a statement is executed and in the precondition the invariant holds, that this invariant from the postcondition holds after the statement is executed. So this is what you usually call an inductive invariant for a program. And this is the first OR triple that we need to prove, the first verification condition. And if we have multiple parallel threads, we also need to show something that is often called non-interference. We need to show that if another thread runs the statement, that this doesn't affect the validity of our local invariant, that doesn't destroy our own local invariant. And so the precondition is that the local invariant holds, and the postcondition is also that the local invariant holds for thread 1. And thread 2 is the one that does the step, and we also know that the precondition of the second thread holds. So we can use this information from the second thread here to show non-interference. And if we prove both inductivity and non-interference, then we have a thread modular proof. And it's also called an Owicki-Gries proof. And now we see that by symmetry, doing this for thread T1 and T2 is sufficient to prove it for arbitrarily many threads. Because it would also hold if a thread T3, the non-interference property for thread T3 would be the same as for thread T2. And if it holds for T2, it also holds for T3. And then it holds for arbitrarily many threads. So this is a proof that works for all threads.
Okay, but it's not given that you can prove any property with a straight modular proof. Right?
Yeah. So yes, this is problematic. So in this case, for example, we cannot even state the property that two threads are in the critical section, because this is not a thread local property here. But at least we may prove that, for example, the ticket dispenser number is always greater equal than the number on the display. So there's a problem if the ticket dispenser, if the tickets that you draw are too small, then you can enter the critical section immediately and then the property wouldn't hold. So here we would like to prove something that S is smaller equal T, and we could try this. So this would be a possible thread modular proof for this. Yeah, initially S is equal to T, so S should be smaller equal T. And if we draw a ticket number, we even know that the next ticket is always greater than our ticket number, which is smaller equal to the displayed number S. And once we enter the critical section, we therefore know that T is strictly greater than S, and when we increment S, then the invariant holds again as smaller equal T. And yeah, we can check inductivity, and yeah, it holds if we use this annotation. For non-interference, yeah, we have to check this T++, and this is why I put here smaller equal. So with T++, this would not interfere here, because increasing T would not make this property wrong. This second statement where we wait is also okay, but the third statement where we increase S may be problematic. And in fact, we cannot show that non-interference holds, for example, for S smaller T. If both are in the critical section, which we cannot exclude from the invariant, and the third thread executes S++, it would invalidate the invariant of the first thread. So this is basically answers your question, can we always do it? In this case, it doesn't work. And in fact, there is no thread modular proof for ticket without auxiliary variables. With auxiliary variables, it may work, but here it's even difficult with auxiliary variables. You need to, I think you need to argue about the set of tickets that are currently distributed around the threads. So you need some set reasoning, and we don't want to use this complicated proofs. So what else can we do? So we can also verify the program for n equals 2. And we look at the interleaved program, and in the interleaved program, we now have 3 times 3 states, so the number of states increases, and we can again find an inductive invariant by annotating every location in our proof with an invariant. And in this case, we may find these invariants, and they are inductive, and they even prove that no 2 threads are in the critical section, because this location where both are critical is annotated as false. So we have proved our property that our ticket algorithm is correct. However, this proof only works for the case of 2 threads. And if we want to prove it for 3 threads, we would need to have 27 states, and we quickly run into the state explosion problem. So we have these 2 kind of proof systems. The first one, thread modular, well, it's polynomial in the size of threads, very small proofs. The proof is valid for arbitrarily many threads because of symmetry. We can argue that if it holds for 2 threads, it holds for arbitrarily many. Unfortunately, it's incomplete, and we cannot prove the ticket algorithm. And the second proof method is this explicit parallel product, where we have this exact analysis. It's exponential in the number of threads. And we only have to prove it for a fixed number of threads. So if we want to show that it's okay with 10 customers, we would need to prove it for these 3 to the power of 10 states and find these invariants for this. And this is very difficult. So is there a middle way, a better way, a way to combine these two approaches? Maybe. And this is where our method comes in, this thread modularity on many levels. And in this case, we look at thread modularity on level 2. And basically, this is the main idea of this talk and probably the slide that you should remember from this talk. So thread modularity on level 2 means you build the cross product of 2 threads. So level 2, therefore 2 threads. And you find an inductive invariant for these 2 threads. And then you put 1 thread in parallel to these 2 threads and ask if this 3rd thread is non-interfering with the 2 threads that you already have. So you basically do this Wiki-Grease method, show the inductivity of your invariance, but you do it on the cross product of 2 threads. And then you take a 3rd thread and then ask, does it, if the invariant holds for these 2 threads and we execute the statement, does the invariant still hold after executing this statement of the 3rd thread, which may change the global variables. And again, you can use some kind of precondition, and the question is, which precondition do you use here? So there is no annotation of the 3rd thread here, and you probably don't want another set of invariants, but you want to reuse these invariants that you have for the 2 threads. And the way you do it is you basically replace the 3rd thread for the 1st and the 2nd thread in the invariant. So you basically have 3 preconditions now. You have the precondition that the invariant for the 1st and 2nd thread holds. Then you also know that the invariant for the 1st and 3rd thread holds. And you know that the invariant for the 2nd and the 3rd thread holds. So you take any combination of these 3 threads and put them and use all the preconditions. And by using all these preconditions, you have a lot of information that may allow you to show non-interference here. Yeah, and this is the basic idea of thread modularity of level 2. And now we can try to prove that ticket is correct for arbitrary many threads by showing that the invariant that we got in the last slide are actually non-interfering with the 3rd thread. Yeah, and again, we see that, well, if we execute the t++ statement, then t will only grow, so the smaller equal t will still hold. The second statement that just checks if s is greater equal t doesn't change any variables, so it will not interfere with any of the invariants that we already have. And for the last statement, the s++, we can now use the extra information that we have. So for example, for all these invariants here at the bottom, something nice happens because there is 1 thread already in the critical section here. And we know that the invariant should also hold when we consider the 3rd thread with the 1st thread, for example. So if the 1st thread is in the critical section, like in these states, and the 3rd thread is in the critical section, we have false in the precondition. And this false in the precondition will tell us that the non-interference property holds trivially. And it holds trivially because if the invariant is correct, then we know that the 2 threads can't be in the critical section at the same time. So this cannot even occur that the 3rd thread executes this s++ statement. And similar for the case where the 1 thread is in the waiting state, and we want to show that s smaller equal n1 is invariant. then we know that if we combine the first thread and the third thread, that S is smaller than M1. So increasing S will still, after increasing S will still smaller equal M1. And so this shows that, this statement is non-interfering with all the invariants, and we have shown that ticket is correct for arbitrary number of steps of threads. And if level 2 is not enough, we can also do it on any other level. So we can do it on level K, where we have an invariant that talks about K threads and over the local variable of K threads. And then we need to show inductivity for any of these K threads that are appearing in our invariant. And then we need to show non-interference with the K+1 thread. And we need to show that executing its statement will not invalidate the invariant for K threads. And then we can add all the preconditions where we replace the K+1 thread with one of the threads. So this formula is quite big, but if you don't need all the preconditions, you can, of course, remove some of them. It only helps you to improve the property. And instead of using horn clauses, instead of using Hort triples, you can also use horn clauses for this. So the difference is that you now have a predicate invariant, which is basically the predicate that you want to solve your horn clause for. You assume that your statements are given as a relation between the pre and post state with unprimed and primed variables, and then the primed variables are here inserted at the right position in the invariant in the post state. And then you have these two predicates, and now you can put it into a horn clause solver and try to find the invariant automatically.
Question, please.
Yeah.
So can you say a bit more about the argument that you use to generalize from K to arbitrary N, or from 2 to arbitrary N? You said by symmetry, but
I think I will shortly say something to this later. Maybe we move it to them.
I'll wait a little bit.
But the main reason is the symmetry, because if it holds for a third, if it's invariant with the third thread, it's also invariant with the fourth thread by symmetry, because the fourth thread will do the same thing. And in every step, only one thread will run. And so this should hold.
Yeah, I could imagine an algorithm where you arrange processes in a tree, for example, and then I guess it's not going to be symmetric from some definition of symmetric, but
yeah, it's really important here that all threads execute the same program. And the invariant needs to basically, this invariant itself is also symmetric, so you can swap the processes around. So one thing is the invariant should be symmetric, and it's probably easier to encode this explicitly. So you can encode that the invariant, you can use this implication that says if the invariance holds for one ordering of the thread, it holds for any other ordering. And if you do this, you only need inductivity for the first thread, and then you can reorder these threads around. And it makes the horn clause derivations a bit longer, because you always need to use symmetry again. But the advantage is that you only have one inductivity horn clause for every statement, instead of one for every statement in every thread that you had before. Yeah, why is it so? This unprovability at level K can be witnessed by a horn clause derivation. There's a remark here. So if you cannot find an invariant for K threads, then you actually see this in the by a counterexample, you basically see something that is very similar to a trace of your program that leads to the error location. But this trace basically uses these non-interfering clauses. So at this point, this horn clause derivation will follow basically several possible paths to this. Yeah, you basically need to show that the invariant holds for the third thread. And then you, if you follow this backwards, you also look which step the third thread does to get to this error location. And yeah, altogether, you find a concrete error path that tells you that unprovability at level k, that the thing is unprovable at level k. And this is also what we use to show that ticket is not, has not a one-thread modular proof.
When you say it can be witnessed, do you mean is it decidable or not?
The problem is that horn clause solving is not decidable. It's semi. So if you have linear arithmetic, then it's semi-decidable that there is a counterexample. So you can guess the error path and then
okay, but you're not guaranteed
get a simple formula that you can decide.
Okay.
But but if you don't find such a counterexample, you never know if it's because your invariant engine is too weak or if there is a counterexample that is just longer. Yeah, so why is it correct? So another way to see it is the Ashcroft invariant, a global invariant, and we call it Ashcroft invariant with K, and it has the form that it quantifies over all the thread indices or over K thread indices from the set 1 to n. And then it states an invariant that for all thread indices that you pick out, this invariant holds. So this is a way to give a global invariant for a system like ticket. And then you need only to prove that this global invariant is inductive. And if you compare this to the thread modular proof, then yeah, you can see that it's basically the same as the K-thread modular proof. So this invariant phi is basically the same thing that you would get from the horn clause solver. So if you get from the horn clause solver some invariant, you can put it into the Ashcroft invariant, and then you have a global invariant of your system. And to show that it's a global invariant, you need to show that for all T1 to Tk this holds in the post state after a step. And then you need to make case distinction which process did the step and what is T1 to Tk. And if the process that did the step is one of the T1 to Tk, then you basically have it by induction. And if the process that did the step is not one of the T1 to Tk, then you have it by non-interference. That this still holds. So this is basically the way we prove that our system is correct and our proof system is correct, and that it's, and you can also show the other way around, that if you have an Ashcroft invariant, you also have an invariant for K-thread modular proofs, and it's almost the same, but you need to build the symmetric closure of the Ashcroft invariant. Yeah, this leads to a kind of hierarchy. So we have seen that ticket is 2-thread modular. It can be proved with 2 threads, but it cannot be proved with 1 thread. So you can ask, is this a strict relation? So does it always help to add more threads? And we showed in the paper that yes, we can, for every K, we can give a thread template that is K-thread modular, but not K-1 thread modular. And we can even find some thread template that is not K-thread modular for any K. And yeah, unfortunately, it's not complete. And the example is also not very difficult, but yeah, we cannot prove programs of this form. What we showed is it's complete for finite thread state thread templates. So yeah, if they don't use integers, but only a finite range of integers or Boolean variables, then it's complete. But the completeness proof doesn't really give an upper bound for this. So it's larger than the number of states in the thread template. So yeah, to summarize the first part of this talk, yeah, we have this K-thread modular proof system, and we showed that this is equivalent to uniform Ashcroft invariance with K. And some corollary is also that if we have a Ashcroft invariant for the product of K+1 threads, then the same Ashcroft invariant is also true for the product of n threads for any larger n. It's kind of astonishing the first time you hear it, but the reason is the symmetry. If it works with a K plus first thread without really talking about the K plus first thread, it works with any additional thread. So there are some limitations in our system. So we don't have thread identifiers, and this is necessary for symmetry. If we had the thread identifier, that would not be enough to show inductivity for thread 1. If we would use that it's thread 1. And also we wouldn't get it for an arbitrary n. And also another limitation is that every thread has to execute the same program, also for symmetry. And yeah, the reason it's called non-proper limitation is because, well, these limitations are not really limitations. We can work around them. So if we want thread identifiers, we can just add them as local variables. So we introduce a global variable n and a local variable tid. And then the first instruction in our thread template is basically the one that we already know from the ticket algorithm. Every thread takes a ticket, it chooses an ID, it sets its ID to n and atomically increases n. And by this, every thread now has a thread ID. And also the global variable n will tell us how many threads are currently active. So in this case, the n can even grow at runtime. But yeah, if you don't want it, you can also use some global variables that indicate that now from now on no new thread should start, and then you can even make sure that n is the number of threads in your program and doesn't change after you started your program. Yeah, the second limitation, every thread has to execute the same program, can be worked around by using the thread IDs and just saying, yeah, if we want one master thread and several slave threads, we can use program like template like this, where we say if the thread ID is 0, we execute one thread. If the thread ID is different from 0, we execute another thread. Yeah, to really show that this method of compositional proofs is practical for real-world applications, we looked into a larger case study, and for this we used the translation look-aside buffer consistency problem. So as you can see from the pics, it's a paper that is quite old. It's from 1989, and yeah. It's called translation look-aside buffer consistency, a software approach. And yeah, it discusses this consistency problem for multiprocessors. It introduces the algorithm that is used in the MAC operation system for maintaining the TLB consistency. It's implemented and runs on, works on real world hardware. I think the MAC operation system is still around, and it's probably also the basis of, it was at least at that time the basis of several microkernel operating systems. So so we thought, let's try this algorithm and see if our method works for this. So to explain what this algorithm is about, we need to understand TLBs and the TLB consistency problem. So first, modern processors, even in 1989, have virtual memory. So this means that the processors that run on the processor think they have a contiguous area of memory where they can write and read from, but the physical memory is really scattered around, and the operating system is moving it from between main memory and hard disk, swapping out pages and swapping them in a transparent fashion. And to implement this, there is some hardware support so that maps virtual addresses to real addresses. So there is a page map, and the page map is read by the hardware to map the virtual to the real addresses. And to make it fast, the hardware must also cache the page map, or at least the part of the page map that is currently important for the program, because otherwise you would need 3 memory accesses instead of 1 in every step, and that would be much too slow. So there is a cache for this, and this is called the TLB, the translation look-aside buffer. It's just caches some entries from the page map that are currently very much used. And this TLB must be invalidated when the page map changes. So if the operating system changes the page map, the hardware doesn't really notice it. And so to be consistent, the operating system must tell the processor, now flush the TLB and reload the entries in there. And this works fine on single processor machines, but on multi-processor machines, you have the TLB consistency problem. So one CPU changes the page map, but the page map is in use by another CPU, and now you need to somehow tell the other CPU to invalidate the TLB. And usually there is no communication between these processors where you can just write into the TLB of the other processor. This would be far too complicated. There were hardware solutions discussed, but here in this paper, this is about a software solution, and it works by sending the other processor an interrupt and then having some code on the other processor in the interrupt handling routine that will flush the TLB cache at the right time. Yeah, and the way it works in the MAC operating system, this is the MAC TLB shoot-down algorithm. This is what I want to explain on this slide. So we have multiple CPUs, and I have drawn one CPU with a page table which contains some entries, and some of these entries are currently cached in the TLB. And we have a second CPU, and this can have the same page table, it can have a different page table. Here we assume it has a different one, it doesn't really matter. But it wants to write to the page table that is currently used by the first processor. What it does, it first locks the page table, but this is not enough because the hardware doesn't know about the locks. The locks are purely implemented in software, and the hardware will still read the page table and assume that everything is okay. So the next step, and this is a part of the TLB shoot down, is that the CPU2 sends an interrupt to the first CPU and tells it needs to stop and wait until the page map is updated. And the CPU will catch this interrupt, and the interrupt handler in the CPU1 will then set a global flag that tells the CPU2 that it's now stopped. So the CPU2 can now write to the TLB, unlock the TLB when it's done, and this unlock operation is visible by CPU1, and it will wait for this unlock, and when it sees this unlock, it will actually flush its TLB, and then both processes can continue. And if there are more than 2 processors, then they also need to be interrupted, and the CPU2 needs to wait on all of them. Yeah, so this is the algorithm. Here's the pseudocode from the paper. It's not too large, so you can imagine that it's still possible to implement something like this. It's more than 3 locations, but yeah, doesn't look too bad. But if you look closer to it, there are some challenges in this. So first, there's some pseudocode high-level functions. You have something like for every CPU in the system. Well, we can easily handle this by this thread identifier trick, where we have the global variable that tells us how many threads we have, and then we iterate over all the threads, and this is possible. Then we have these log action structure. We have logs and in this pseudocode, and we implement them by Boolean variables that are automatically written to true. They are checked for being false and then automatically set to true in the log operating. So this is also something that we can handle. Then there are some queues. There are lots of variables, and here we simplified it a bit and assume that that always the whole TLB is flushed. So instead of queuing some actions to flush some parts of the TLB, we only queue the action to flush the whole TLB, and then we can use a Boolean variable here. Next challenges are that the code is incomplete because it doesn't contain the code for the hardware. So in the code, there's a send shoot down interrupt, and this will, of course, change the behavior of the other processors in some way. And this is not given in the pseudocode. So we somehow have to also model the hardware. And the last point is there is no specification. So we have to come up with a specification. So to solve the last 2 problems, we introduced the test harness. So we have a main loop. This main loop also contains a specification, namely that while we are in the main loop, the TLB is always consistent. And it handles the interrupts. So if it sees there is an interrupt, then it calls the interrupt routine, the responder. And it also can non-deterministically at any time call the initiator, which in the paper is the one that changes an entry on the page map. So here we allow arbitrarily many processes change different page maps at the same time. And to handle these interrupts and shoot down interrupt, we just set this interrupt flag to true. And yeah, you see there's here a global array interrupt that is shared between all threads. So we have here an interrupt. And arrays are complicated, and we probably need quantified invariants, and we want to avoid all of that. And what we really would like to have is that interrupt is a local variable. But this is not really possible because we write here the interrupt of a different CPU and set it to true. And after thinking about it, we came to a solution for this that is quite nice. And one could call it implementing arrays without arrays. So instead of having global arrays, we have local variables, and the arrays are implemented by local variables. And each thread contains one cell of the array. And we do read-write by using synchronized statements that change the local variables of more than one thread. So 2 threads basically communicate. One thread is really driving the action. It wants to write something. Here's an example. Here we have one thread that wants to set the interrupt cell to true of a CPU that may be a different one. And we implement it by this pseudocode where we say, thread 1 is the one that drives everything. So we assume its program counter is init 8, and afterwards we set it to init 9. And if it happens that thread 1 is also the one that the CPU points to, then we can just write the local variable of thread 1. But if it isn't, we assume that thread 2 is the one. And then we write the local variable of thread 2. And now the scheduler can basically pick 2 threads and check if they are executable. And if they are executable, it can execute them. And by this, we get the correct semantics for these array writes. And similarly, we can do array reads. And this works very nice in our system. We need to change the verification conditions a bit, especially the non-interference ones. So for inductivity, we now have 2 threads, but we can, again, by symmetry, assume that it's always the first and the second thread that are running. And the non-interference basically handles the case where a third thread is running together with the first thread or together with the second thread. And by symmetry, we can always assume that it's running together with the first thread. So the third thread is here, x0, that is running with x1. And then we have 2 cases that x0 is the one that's basically called process 1 here in this pseudocode, or that x0 is the one that is called process 2 in the pseudocode. And yeah, we can even extend this for k threads if we want to do it for k thread modularity. And yeah, this way we encoded the whole shootdown protocol. We have 23 program locations. We did it for k equals 2. 1 global variable, 12 local variable, a lot of horn clauses, 60 in total. And then we fed it into an horn clause solver. And yeah, it doesn't work. So the system is too large for automatic invariant generation. We encoded the candidate invariant manually, automatically checked it, and reiterated it. So we used v3 to check it. And if it doesn't hold, then we change the candidate invariant. And finally, we found a schedule that violates consistency. And yeah, we asked ourselves, is this a problem with the old paper or is it our implementation? So this is where the problem is in the old paper.
So could it also be that k was not high enough?
So, sorry?
Could it also be that you choose a too low k?
It actually, in this case, it could be in theory, but we could actually simulate this on 2 threads, I think. It was possible to do it without the interference things. So we could even use it without, we didn't need an interference clause for this schedule. So we know that already 2 threads are not safe.
Okay. So you see that in the counterexample that you get.
Yeah. Actually, we didn't get the count example, but we found it manually. So the count example is something like 40 steps, and the automatic method couldn't find it. And yeah, looking at the context or looking at the problem in the interrupt handler, it's somewhere here. You may spot it if you look closer to this code. So how does it work? The interrupt handler is called when another thread changes the PMAP, the other thread locks the PMAP, calls the interrupt handler, and the interrupt handler now waits until the PMAP is unlocked in this bin loop. And once it's unlocked, it's locked the action structure, flushes the TLB, does the rest, and unlocks the action structure, and is done. And yeah, if you look close to this, there is a yield point in between these 2 statements. So it can happen that the interrupt handler sees the PMAP is unlocked, exits the while loop, and in this moment, the other processors will lock the PMAP again, change something in the action structure, and before this action structure is locked, they will change something, and then the whole consistency is no longer guaranteed. So the problem is basically there is one yield point here before the action structure is locked, where the other threads may interfere. So we wondered, is this really a problem? Or is this a problem in the ordinary algorithm? So we asked some expert, and we got a nice reply from David Black, a potential bug report on pseudocode in a 25-plus-year-old paper. That's certainly something unexpected in my inbox. Yeah, so he now argues, it looks like the verification technique may have assumed that arbitrary timing delays are possible between steps. Yes, we did assume this, and our counterexample basically showed this. Whereas one of the reasons that the algorithm disables interrupts is to prevent those sorts of delays. And with modern processor virtualization techniques, you may have a point. So to conclude, it's not a bug for the hardware for which the technique was designed. So this was designed in 1989. Hardware was easy, and memory wasn't a very complicated thing. And one has to consider this with the interrupts. So the interrupts are basically local to one processor. So if one processor disables the interrupt, the other processors can still do things, but the important thing here is the timing. So it's not possible for a processor to need so long time to do this lock action structure when the interrupts are disabled, that another processor can lock another PMAP, do some operations, and then lock the action structure before this processor has a chance. But with virtual machines, this can happen because there is no timing guarantees between these processes. Yeah, so don't run a mock operation system on a VirtualBox, or you may run into this problem. So the way we fixed it is we made the statement atomic. So we removed the schedule point. We also asserted that the action structure is not locked at this time, so that the lock operation will not block here. And after this change, we basically restarted it. Our proof thought it's still too large for automatic invariant generation. We tried some manual encoding, we automatically checked it, and finally we found one. And yeah, it's quite big, but maybe not too big, but it's quite tricky. So there is a reason it cannot be found automatically. And here's an excerpt from this. The invariant is for k equals 2. And what I want to note here is, even though it's for k equals 2 and uses only variables from two processes, these processes change their role in every conjunct. So the first conjunct here talks about a process between init2 and init14, and the second process that is a process that stores a plock variable of pmap. Yeah, the code here between init2 and init14 is some critical region, so it's locked with a plock pmap, and this is this array, and the array cell plock is stored in the process number 2 here. And this basically states while we are in the critical region, the lock variable is true. And the second here says that if two processes are in the critical region, their pmap variable is different. And the important thing to notice here is that the second process here is not the same as the second process here. So even though each conjunct only talks about two processes, the invariant somehow, even though it just says end here, talks about a lot of processes at the same time. And yeah, even the third process. Yeah, the proof is valid for arbitrarily many processors. And there can be more than one initiator. We have this non-deterministic choice where every processor can choose to be initiated at any time. And it even supports adding more processes at runtime. We get it for free because of our way we implement it. So, and I think this is the first proof of this algorithm, because otherwise someone would probably have found this problem, this timing problem that is undocumented earlier. Yeah, so yeah, one remark, I'm not sure, I can shortly talk about it. We have seen that we have these array programs that we implemented the arrays by parallel processes, and this can be generalized. We can even prove sequential array programs using this trick. So basically, we have one thread 0 that executes the program, and the other threads are only there to store the array sets. And then there's a theorem that if there is a quantified array invariant with k, then we can use a k+1 thread modular proof. The plus one is because of thread 0 that executes the program. So this shows that we can also prove something like bubble sort or quick sort or merge sort with this method. Yeah, to come to a conclusion, yeah, this was thread modularity, and you can do it on several levels by building the cross product in a limited way, and then show that this cross product is non-interfering with another process, with another parallel process. We have yeah, it's polynomial in the size of the system, but yeah, it gets quite big. So for these 23 locations and 2 threads, we already have something like 500 locations. And if we didn't use this trick by using basically encoding program counter ranges with this PC is smaller equal than some statement and greater equal some other statement, I think the manual invariant would be much longer. We found that k=2 works well. It's this kind of sweet spot between expressivity and complexity. And yeah, we need better horned loss solvers. So ticket algorithm is provable, or it's barely provable. It takes some time, but I think the invariant can be found automatically. But for something like that is larger than 3 statements, it's even with k=2, it doesn't work. Okay, so thank you.
Okay, thank you. Very interesting talk. We're already a bit past 5, but we started late, so maybe we have time for 1 or 2 questions. Just speak up if you want. Don't have anything in the chat.
And so maybe one question from me. So initially you said, you can't use thread IDs, and then afterwards you had this slide where you said, well, in fact we can. Here's a simple trick that works. So this was a little surprising. So is there something that's lost with this trick? Like, can it really express every algorithm that's going to be using thread IDs? Or?
I think it should work. So basically the trick is now that you, if you look in the invariant, you always need to say something like the thread ID of 2 is equal to some global variable, and yeah, basically this PID 2 will, instead of just writing 2 is equal to pmap, which you would do if you had thread IDs somehow encoded, you need to write PID 2 is equal to pmap. And then and the advantage is that it works for, the invariant is now symmetric because it doesn't, yeah, it doesn't really matter which value this PID has, whether it's 2 or whether it's a larger number. And so I don't think there should be a limitation.
So let's say I have an algorithm like I was saying earlier, where processes arrange themselves in a tree according to their PID. So I guess using this trick, we can make it symmetric.
Yeah.
But then probably the k will be very high, or maybe since it's not complete, there's not going to be any k that will work. Is that correct?
I'm not sure what you mean by tree. So if the processes communicate in a kind of tree,
yeah, for example.
and you of course need to encode this somehow in your program. You must say that the process that I communicate with has a thread ID that is computed somehow by some linear operation.
Right.
And this will probably also reflect in the invariant and makes this probably harder.
Yeah. Yeah, and so in this case, maybe since your method is not complete, it's possible that no K will work, right? Even if my algorithm is correct.
Yes. Yeah, it can happen.
Yeah.
It depends on the algorithm. So we have very simple algorithm where it doesn't work. The simplest one is you do x plus plus, x minus minus in parallel in n threads, and then your invariant is x is always greater equal 0. And you can't prove it. And the reason is that you need to somehow state that x is larger than the number of processes that are in the location between the x plus plus and the x minus minus. So you have to count processes, and this method can't count. It can only say there is a process that there or there is not a process. It can count up to k by saying there are k processes.
Right.
Okay, I think we should move on. Thanks again for the talk. So Srija is next. You should already be able to, yeah. Okay, yeah, so next up is Srija Nair, and she's talking about the coordination lattice. Curious what that is about. So, the floor is yours, you're still muted.
Can you hear me now?
Yes, but we don't see the
Okay.
slides anymore.
Perfect. Yeah,
Yes.
I hope you see it now.
Yep.
Okay, so thank you for the introduction. And today I'll be talking about the selection of concurrency control algorithms for distributed applications. So I'll be taking a small deviation from the workshop topic as such, because I will be using the results of formal reasoning and seeing like how we can do performance improvements on top of it. So I think that will be interesting for the audience. So let's start. Okay, so first let's consider a centralized web application that serves users across several geographical regions. All users from all locations are connected to a single replica, and the perceived latency for the distant user is very high. So in order to lower the latency, the centralized object is distributed into like 3 different replicas across different continents. And now users are connected to the nearest replica. This actually ensures that we provide low latency service to the users. But unfortunately, this situation gives rise to concurrency bugs. So I'll show you an example of like how concurrency might violate an invariant. So let us examine an example of a distributed auction. Assume we have like 3 different replicas distributed across the globe, and different users are connected to them. So a user, Srija, that's me, who is connected to a replica in Asia, has a painting which he has to put up for an auction. The green dot near the painting indicates that the auction is open to receive bids. Srija opens the auction, and this state is propagated to Mark and Gustavo, who are connected to the European and American replicas, respectively. So Gustavo sees Mark's, both of them are interested in the painting, and Mark placed the first bid for 100 euros. This state is being propagated to both Srija and Gustavo. Now, Gustavo sees Mark's bid, and he wants to place a higher bid for 105 euros. Unfortunately, at the same time, the connection between the replicas in Asia and South America broke down. So Gustavo's higher bid was propagated to Mark, but unfortunately not to Srija. Meanwhile, Srija, unaware of Gustavo's bid, was happy with Mark's bid itself. So she decides to close an auction and declare Mark's €100 bid as the winner. So when now this state is also propagated to Mark, he sees that, okay, he won, which he should be happy, but actually the application invariant for the auction example, for auction is being violated here because his bid is the lowest bid and it won. So this is a violation of the invariant of a distributed auction that requires the highest bid to win. So what can we do? We can make use of some static analysis, which is actually, I have developed a static analysis, which was published in ESOP last year, ESOP 2020. So using that static analysis tools, we can identify like what are the conflicts in an auction application. So when we run the auction example, I mean, a trivialized auction example, not the full-fledged application one, through the static analysis, we find that, okay, we have a set of conflicts which we can detect. Basically, we see that there is a conflict between concurrently placing a bid while closing an auction, which we just saw in the previous example, which happens for a single auction. So, I mean, if we are placing a bid for placing a bid and the same auction is being concurrently closed, we might run into an application invariant violation. So similarly, we also detected conflicts for a concurrent place bid and unregistered buyer, where the buyer who is actually placing the bid was being unregistered from a remote replicant. And we also have issues with concurrently closing an auction and removing a bid. Maybe the bid being removed might have been the highest bid, so it would have been selected as a winner. So now how should we move forward from here? Because now we have the results from the formal reasoning of the distributed application, and how should we take that forward? So there are actually several different ways to introduce coordination into a distributed application. We can say like, okay, let all the conflicts take mutual exclusion. So well and good, everything is safe, so we are happy. But in case of an application, this might come up with, I mean, there might be performance implications as well. So as to be useful to the application developers. So in this work, actually, I looked into like distributed locking, only distributed locking, and I tried to like dig a bit more deeper into like what are the properties that we can look into for selecting an optimal distributed lock configuration. So let us now discuss the properties which we can look into and how the dynamic characteristics of the application and also the constraints imposed by us might affect the selection. So if you think about like selecting efficient concurrency control when we have safety in mind, on one hand, we have a set of constraints imposed on us by the application and the system on top of which the application is running. On the other hand, we have some parameters for a distributed lock that we can manipulate such that we obtain the optimal performance under the set constraints. So the constraints imposed upon us are mainly, the first thing is coordination, which is needed to ensure safety, which we get from the formal reasoning. The second is the dynamic characteristics of the application, namely the workload characteristics. The system constraint, which is basically like the network latency. So we saw that the system is distributed across the globe. So there will be a definite latency between different replicas, and also the implicit cost of locking. So we will go through it like one by one.
Just a question?
Sure.
So by coordination to ensure safety here, I presume you mean to not violate your application level invariant that you were talking about, right?
Exactly. So we actually like have a formal result from, so we have the results from the formal reasoning from the previous step regarding like which kind of conflicts we need to handle. So we have a set of conflicts between pairs of operations, and we need to somehow coordinate between them to ensure safety.
And so for each conflict, you know that you need a mutual exclusion, or?
We have to identify which one. So that's the work. That's what the work is about.
Okay.
So we just need know like these are the pair of operations that conflict. That's it. That's all we know as of now. And we have to see like how each parameter and how each constraint might affect the choice on like whether we should go for a shared exclusive lock or we should go for a mutual exclusive lock and some other parameters as well. I'll walk you through like the details.
Okay.
So, as I was telling, like we have a set of constraints, and despite all these constraints, even though we have to still keep them in mind, we also have like a set of variables that we can control. Basically, it's parameters that we could manipulate so that we can achieve better performance. So, what are them? One thing is like granularity. So we can maybe use fine-grained locks, or we can coarsen the locks together. So we can vary across the granularity dimension. The second thing is like we can choose the type of lock. And as you mentioned, like we can choose either we should go for mutual exclusion or we should we go for a shared exclusive mode of locking, which one. And also we in a distributed application is also important that we have to look into the placement of locks. So basically where we should physically place the lock service. So all these are like variables that we can control because we as I mean by we I mean application developers can control so that they achieve they have the best performance for their application. So let's now first look into like different constraints one by one. So first, let us look at the safety constraint. So as we saw, like we previously saw, like we have pairs of operations that are conflicting. Basically, we had a conflict between placing a bid and closing an auction concurrently. We had another conflict between placing a bid and unregistering a buyer, and we had a third conflict between closing an auction and removing a bid. Sorry. So we try to like, so we know that, okay, we should somehow introduce some coordination to ensure safety here in this scenario. So what the first step we can do is take the list of conflicts and try to map them as a conflict graph. So here in this particular graph, we can see that, do you see my pointer? Okay.
No, I don't see it.
I guess I'm unable to point it. Let's forget about it. So we can see that in the left hand down, we can see I mean, in the conflict graph, like each boxes represent an operation and the edges between them represent the conflict. So the labels on the edges indicates like on which parameter actually they have to coordinate. So we can see like place, bid, and close auction, which are the bottom two operations, need to coordinate on a given auction so as to remain safe. And likewise, close auction and remove bid should also coordinate on a single auction, and place bid and unregister buyer should coordinate on buyer parameter. So basically, like this is the first step of representing the the safety constraints as a conflict graph. Now we need to ensure coordination according to this conflict graph. And just as a reminder, in this talk, actually, we will be focusing only on distributed locks, even though there are like different coordination mechanisms out there. This work is only focusing on distributed locks. So the next constraint we have is the dynamic constraint of the application, namely the workload. So the workload can be skewed both in frequency per operation or frequency per replica as well. Basically, like frequency of an operation per replica. So let's consider the same conflict graph that we saw earlier, which includes like the 4 operations. Placing a bid would be the most frequent among these operations. Like as we have a mental picture about an auction application, there will be like frequent place bids than unregistering a buyer or closing an auction or even removing a bid. So we can here see that, okay, there is a very high skew on the frequency per operation. There is a small probability for the other 3 operations as well, even though it's sparse. So I just, the numbers are kind of made up just to show that, okay, there is a definite skew. And now let's zoom into the place bit operation and see the location from which the operations are being issued. So the right-hand side actually shows the physical placement of the replicas. So assume like one replica was placed in Paris, one in Singapore, and the third one in Houston. So, and consider maybe, since Paris is famous for baguettes, I'm taking an example of a baguette making machine. So if I'm putting up a baguette making machine for an auction, of course, maybe 95% of the bids might be from Paris. And there might be 5% of the bids from Houston, and maybe no one is interested in Singapore to buy a baguette making machine. So actually this depicts a skew in the frequency of an operation, depending on the location as well. So that's what I meant by a skew in the frequency per replica. So this is the second constraint which we showed. And the third constraint is basically the introduced due to the network. So as we saw that the three replicas are like geographically distributed across Paris, Houston, and Singapore, there will be a definite network latency between those replicas. So assume like a client was in Houston and the lock service is in Singapore. So the client will have to like do a round trip to Singapore to acquire the lock, and another round trip to let them know like, okay, I've released the lock as well. So this actually adds into the application latency as well. So this is the third constraint imposed on the system. And we also have to keep this in mind while selecting a distributed lock. So
another question, please.
Sure.
So when you say the client will have to take the locks, you mean that, so let's say I place a bid, then I'm going to have to take the lock, and then once I acquire it, not release it until everybody has received my bid. Is that correct?
Yes, exactly. Like it depends actually. So if you're looking for a shared exclusive mode of locking, you can acquire a shared mode of lock and then go on placing several bits. And when you release the lock, you have to like ensure that all the set of bits are being propagated as well with the lock release message. So that means like we get kind of a snapshots in the history when we acquire and release locks.
Okay.
But it can be kind of optimized, like, okay, a replica can, in the replica level, acquire a lock and keep it for some time. So there might be like different, I mean, practical implementations of it. But now I'm trying to like look at the metrics on which we can guide the choice.
Yep. Makes sense.
Okay. So the fourth and the kind of the last constraint which we are looking into is the cost of locking itself. So cost of locking is basically the response time in like the response time. The cost of locking actually contains the response time in acquiring and releasing a lock. So when the distance between the lock services and the user goes on increasing, we can see in the graph also, we can observe that the the cost of locking also increases. So this graph is actually a benchmarking of HCD with client. I mean, the first set of bars shows an exclusive and shared mode of lock when the client and the lock service are co-located. So basically there is zero network latency between them, but we can still see that there's a think time basically for the acquire and release of the lock. And when there is a 55 millisecond latency, like one-way latency between the client and the server, client and the lock service, we can see that there is like a 200 plus, millisecond cost of locking overhead increase. This is because like it has to do several round trips to acquire and release the locks. So here we observe that the cost of lock varies between the distance between the lock service and the client, but remains the same for both modes of locking, or at least like in the case of HCD, where actually for Zookeeper as well. So HCD and Zookeeper are the most commonly used distributed locking services. So I just went with their model of having the same cost of locking for shared and exclusive modes. But when we look at the shared and exclusive mode of locking, we will have a difference in the name of lock contention, and we will come to that later. So right now, it's just only the cost of lock acquisition and release. That's it. So to summarize the constraints, we talked about like 4 constraints. The first one is safety constraint, which requires us to have locks to ensure safety. So that's where we know that, okay, we need locks in these scenarios. The second one is the workload constraint, which shows the dynamic characteristics of the application. Basically, like we saw that, okay, there might be a skew of frequency in per operation and also per replica. Basically locality and frequency skew. And then the third constraint we have is the network constraint, which basically like is tells that, okay, there is a latency between replicas and we can't do anything about it. And the fourth constraint is the cost of lock acquisition, which we call the lock cost constraint. So now let us see like what are the variables that we can manipulate and how manipulating each variable would contribute to the overall performance of the distributed application. So at first we can look at the granularity variable. So you might remember the conflict graph which we just discussed, and the conflict graph we discussed as such is present in the bottom most part of the slide. So where you can see like there are there are 4 operations and 3 conflicts. So basically like we have fine-grained locks, 1 lock between a place bid and unregistered buyer per buyer, 1 lock between place bid and close auction per auction, and a third lock between close auction and remove bid per auction as well. So here we can have like 2 different dimensions of coarsening. So we can either coarsen such that the place bid operation has to occur only a single lock. That's towards the right. So in that case, actually, place bid can occur a lock for both buyer and auction combined, which so internally is shared between close auction and unregistered buyer. So now the 3 operations work share a single lock, and close auction and remove bid shares another lock. So basically, place bid only needs to occur a single lock. The other direction we can coarsen is towards the left in the slide. So we can see that, okay, now the close auction has to occur only a single lock, so which is coarsened on per auction. So now that per auction lock is shared between place bid, close auction, and remove bid, and the buyer lock is shared between place bid and unregistered buyer. So we can further coarsen it such that the entire set of operations in the conflict graph share a single lock. So now basically like all the 4 shares a single lock. So actually there are trade-offs while coarsening and fine graining as well. So we can see like how the granularity dimension will impact our impact the performance of the distributed application. So let's consider let's zoom into place bid. And let's consider 3 different scenarios for place bid. Actually, first of all, had to acquire 2 locks. Then in the second case, where it had to acquire only 1 lock shared between 2 other operations. And in the third case, where it was sharing a single lock with all the operations. So we can see a bit more into like what happens over there. So in the first case, actually, place bid now has to acquire 2 locks. And since we already saw that place bid is the most frequent operation, acquiring 2 locks increases the lock acquisition time. It has to like sequentially acquire each lock. We can obviously try to parallelize it, but it might lead to deadlock. So the best approach is to like sequentially acquire the first lock, and then once we are sure that we have acquired it, go and get the next one. So this actually increases the lock acquisition time, but this gives the lowest possible contention level in the system, because now the locks are not unnecessarily waiting for any other operation to complete. But when we coarsen the place bit such that now the place to the second level, so the middle conflict graph in the slide, which I'm showing. So if we coarsen to that level, we can see like, okay, now the place bit actually has to occur only a single lock. So the lock acquisition time comes down a lot. But now, since unregistered buyer and closed auction, who were not actually waiting for each other in the previous case, now has to wait for each other because they are also sharing the same lock. So in effect, this increases the lock contention in the system. And in the third case, actually, it further worsens because in the place bit, we are not gaining any lock acquisition time because the place bit still only has to occur one lock. But now remove bit also comes into the picture since all the 4 operations are sharing the same lock, so it adds contention. So now we can see like when we coarsen, we are actually increasing the contention, but at the same time we also minimize, the lock acquisition time also comes down. So there is a sweet spot in between them. And we will need to come up with some metrics to identify that sweet spot and it's for selecting the granularity. So now we can go to the next variable, which is the mode of locking. And here is the question which you asked, like whether we should go for mutual exclusion or should we go for shared exclusive. So actually we have several possibilities. Either we can have like, okay, maybe I can show the example here. So the first conflict graph, actually I removed one operation from it so that it's easier to concentrate. So now we have like just 3 operations conflicting on a single lock. And the first configuration I show here is all the operations are occurring the same lock in mutual exclusive mode. So no, there is no parallelism. Every operation has to wait until the other finishes. But if you come to the second part, we can see that place bid and remove bid are still in the exclusive mode of locking, but closed auction is can acquire the shared mode of locking, which improves the parallelism a bit because closed auction now doesn't have to wait for other closed auctions to finish. And if you look at the third option, we can see like, okay, place bid actually has the shared mode and remove bid as well. But closed auction needs to synchronize between both of them. So before closing an auction, we have to make sure that, okay, we have the exclusive mode. So basically there are no other operations that acquire the shared mode and which is going on. So in short, exclusive mode actually introduces contention, whereas a shared mode allows parallel execution. So
does your static analysis tell you which combinations are safe?
No, actually, the static analysis won't tell us which combinations are safe. The static analysis only tells us that, okay, these are the operations that need to coordinate. We have to define a set of metrics that can guide us to choose like which mode to go for. So,
but in some cases, like if all the operations goes for shared, then it might violate application invariance.
Yes, exactly. So how we should select the shared versus exclusive is we take the conflict graph and we select the nodes such that each conflict is I forgot the actual graph theory term of it. It was called maximal click something. I'll just tell you the concept. So it's take the conflict graph and make sure that you select the minimal number of vertices such that all the conflicts are covered. So that set should have, that set should have the exclusive mode of locking at least. So we can make sure that for each conflict, at least one of the operation has an exclusive mode for that lock. So in that case, we don't violate the safety. So I didn't explain that here because I thought like that's actually that's in my thesis. I have written it, but not in the stock, unfortunately. I should have included that. Thank you for
finding it.
So in this
example, they're all good, right? What we see on the slide, but we couldn't have place bid as shared, close auction as shared, and remove bid as exclusive. That would work.
Yeah, so like if, okay, I'll tell you in this particular conflict graph, like, so what would be the algorithm which selects which operations should run exclusive versus which should run parallel. So if you look at this graph, actually, I can cluster this graph into like two components, one which will contain only the close auction and another will contain only the place bid and remove bid. So for both these clusters, what is the most important thing is like for a single cluster, that the set of nodes in that cluster will cover all the conflicts. So for the close auction, actually the close auction shares all the conflicts. So it is safe to only provide exclusive mode for that close auction. So this is actually inbuilt in the part of the algorithm. So that's how I select configurations. And if for the other part, so since I partitioned the graph into two, in the second part, I have like the place bid and remove bid operations. And we can see like the place bid and remove bid also covers all the conflicts. So if we assign exclusive mode, so when we select exclusive mode, we should assign exclusive mode to either of the whole group. So we cannot select handpick some methods from the group and say like, okay, now you go for exclusive and you for shared. No, we have to like select one group of methods from this partition and then assign like, okay, this group goes exclusive and the other group goes shared. So we can exchange that, but we cannot mix the groups. Am I clear now?
Yeah, that makes sense.
Okay,
Thanks.
thank you. So in the case of this particular example, as we saw earlier, like the place bid is the most frequent operation. So I mean, taking a shared mode for place bid makes sense because we can allow maximum parallels as possible. So these are the examples. We'll come into the metrics later on. So now the third variable which we are looking into is actually the lock placement. And as we saw in the lock constraint, the distance between the client and the lock service should be actually kept minimal. So for our example, place bid is the most frequent operation. And since we were talking about a bucket machine, the maximum number of place bids were happening, bids were being placed from Paris. So the best option for us would be to co-locate the lock services like the place bid needs to acquire in Paris. So place bid will acquire the lock, I mean, without any network latency from the local replicate itself. So this will reduce the cost of locking and hence indirectly also benefit for the lock contention as well. So to summarize regarding the variables, while selecting a coordination configuration, when we look for the granularity variable, we are looking into like minimizing the execution time. When looking into the mode variable, we are looking into, we are trying to maximize the parallelism that can be allowed. And while selecting the placement variable, we are trying to minimize the acquisition cost. So now let us try to combine these three dimensions into a single structure so that it's easier for us to navigate. And so we can combine the three dimensions together to form something that we call a coordination lattice. Actually, the granularity dimensions provides the lattice structure. Now let us take a look into the conflict graph of the auction example. So I just here shorten the names of the coordination condition, like B for the buyer, A1 for the first, I mean, a conflict between place bid and close auction instead of auction, and A2 for the conflict between close auction and remove bid. So the right-hand side actually represents the projection of the coordination lattice along the granularity dimension. You can see that the bottommost element in the structure represents the finest locks, basically the fine-grained locks, and the topmost represents the coarsest. So we can see a single box with all the names concatenated, which represents only one lock. The bottom one is divided into, partitioned into like three separate boxes. And the elements in the middle represent the intermediate coarsening, as we saw earlier. So we can call an element in the lattice as a coordination element. We'll take a closer look into the coordination element, specifically on the middle one in the right. So the one which I have pointed to, so which has basically two locks, one on a buyer and the other correspondent over both the options. So a coordination element, as I've shown here, actually consists of sub-elements, and in this case, actually two sub-elements. For each sub-element, we have to choose mode and placement. And we represent the mode and placement in 2 dimensions. For each sub-element, we can select the mode of locking, which basically like which operations get which mode, and also placement. There are different possible configurations for both mode and placement. And for example, in the table on the left-hand side, which represents the mode options for the buyer lock, we can see like the first one, MX, the first row, represents that, okay, mutual exclusion. So basically like both the operations take the lock in exclusive mode. And the second row represents unregistered buyer operation acquiring the lock in exclusive mode, and the place bit happening with shared mode. And the last row does reverse. And on the right hand side, we can see for the correspondent case on like how we have divided the exclusive and shared mode. Basically, we have like 3 different configurations. The first one, the 3 operations take the lock in exclusive mode. And as we discussed, since we are partitioning the graph into 2, the first row shows only a single operation taking the shared mode, and the second row shows 2 operations taking the shared mode. So now we have to decide like which mode from this set of operations can the application developer use so that the performance of the distributed application is the best. So we also have the user also has like several different placement options to choose from. So we try to like represent that in a 2-dimensional plane with the mode and placement axis. And one point in the plane corresponds to the exact coordination configuration for a lock. So both together actually forms the full coordination configuration, because for that particular config graph, actually, since we coarsened into 2 locks, we need to select the mode and placement for both locks to obtain a coordination configuration. So basically, a single coordination configuration is a set of locks with granularity, mode, and placement dimensions. Now, what we also have developed some metrics to help us navigate this coordination lattice. So the first, and the idea is to like minimize the total replica execution time. So in this particular equation shows the average replica execution time. So we basically like take the effect of serialization, which is imposed due to the mode of locking, which we represented as CC op serial. So basically like due to serialization of the operation due to the exclusive mode. And then the second line shows the serialization that is imposed due to the replica. So in this model, actually, we are considering the replica to have only a sequential execution. And the third mode is the third metric actually represents the parallelism allowed by the shared mode of locking. So all these combined together will give us an average of the replica execution time. Actually, cost of locking is impacted by the lock placement, and which is a component inside all these metrics as well. So now with this coordination lattice, I'm going to show you like a few examples on like how well our prediction fares with the actual real world use case. So just consider a super simple config graph which has.
Can you try to do the examples in roughly 3 minutes? Sure,
yeah. I can just skim over it. So we have like 2 operations here working on a single, conflicting on a single, having a single conflict. And so we see that when we look at the workload, we can see that, okay, at a single place, we have 500 operations in Paris, and the Y operation takes place distributed in Houston and Singapore. So we also see the mode and placement dimensions. And here the red line actually indicates our metrics prediction on how the performance should fare. And the blue line indicates actually the total actual execution time, which we get from the experiment results. So we can see like the pattern matches, but there will be a small difference always because the metrics actually predicts the average, whereas the experimental value, we measure the total execution time because it was a bit difficult to get the average. So we can see like, okay, the best thing, so we can also see like the prediction actually predicted the configuration of 122, which is basically granularity level 1, which doesn't make any sense here because it's just a single lock. And the mode of locking 2, where X gets the exclusive mode and Y gets a shared mode, is beneficial. And the lock is being placed at paddis is also beneficial. So what we learned from this is basically co-locate the lock with the workload and choose the shared mode for the most frequently distributed operation. So we can see like even though the frequency of X and Y are the same, Y is more distributed across Houston and Singapore. So it's better to give a shared mode for Y. Now I'll just skim through a bit more complicated example where we have 3 operations as we discussed. And since we can also look at the coarsening dimension. So first of all, I can show you that, okay, Y is the operation that actually shares both the conflicts. And in the workload, we can see the workload is of top right table. And we can see that Y actually has 100 operation each on all the replicas. So we can see here that coarsening Y is actually better. Coarsening for this case for Y is better because the lock acquisition costs come down. And since X and Z are like very rare, we are not increasing any contention in the system. But if there is a difference in the workload, so now we can see like the leftmost table just below the conflict graph represents the workload, where the shared the operation that was sharing the lock basically it doesn't have any I mean there is 0 frequency actually, and the other 2 operations are actually more frequent. So in this case actually sharing coarsening worsens the thing because it increases contention in the system. So what we learn from this is like coordination is a trade-off between contention and acquisition cost. So we have a list of future work to basically include more concurrency control semantics and coming up with a probabilistic model and such that. And so to conclude, coordination lattice is actually a first baby step towards a systematical exploration of the performance implication of concurrency control. And it's a small step towards actually engineering just right consistent distributed applications, because we get what we have to coordinate from the formal reasoning, and then we try to optimize the performance over there. And yeah, that's it. Thanks a lot.
Okay.
So, any questions?
Yeah, pretty cool. Do we have questions? Juliana's already getting ready.
Well, I was thinking that you could probably imagine moving the logs dynamically. Does your system do that, like at runtime?
No, as actually like we are only looking into like static characteristics of the system. And as I told, like this was the first step towards like trying to formalize the performance implications of the distributed locking. There has been no work in this area yet. So the next step actually would be like to look into the dynamics so that we can actually learn from the workload characteristics of the system when it's running, and then dynamically adjust the locks. But it's a very future step, I would say, because this still has like lots of improvements regarding like basically the probability of like 2 operations to occur at the same time and things like that. So yeah, there's a lot of work to be done to be actually kind of useful for people. But this is the first step.
Thanks.
Thank you.
Okay, and the So where formal methods come in here is just in telling you what you can safely select from, or do you see other possibilities where you could?
Yeah, so like in the case of distributed applications, the famous CAP theorem says like, okay, you can either choose for consistency or availability when there is a network partition. So in this case, actually, we are using formal methods to identify like, okay, which is the just right consistency, which we need to maintain. And for that, actually, formal methods come into picture. And the formal methods actually contribute to generating the conflict graph.
Mm-hmm.
And from the conflict graph, then we have to see like, so that was actually the whole work is actually part of my PhD thesis. So my first part of the thesis was to how to get this conflict graph so that we just try to minimize the consistency requirements so that we only need to coordinate just to ensure safety. And the next step was to like look into like how could we use this result forward as to like to make it useful for the programmers so that they can say, okay, use this lock here and in this configuration so that your application can perform well instead of like giving a blind mutual exclusive lock or just randomly selecting a shared exclusive mode or doing some random placement or selecting random granularity. So
yeah, sure. Okay, good. Thank you.
Thank you.
Then yeah, let's have a quick break and meet again at 5:55, so in 6 minutes. Eruption.
Hello.
So Giuliani, you're taking over now?
Yep, I see it's 5:55. Welcome back to FRIDA. So our next speaker will be Kerem Sakala, who's gonna talk about a new approach to verify distributed protocols, and in particular, infer inductive invariance, I believe. Kerem, the floor is yours.
Thank you very much. Let me share my screen. All right, well, good evening to most of you in Europe and afternoon elsewhere. Just want to express my appreciation for being invited to speak at this workshop. And this is going to be different because this is not my usual community. So I hope that this might motivate some collaboration across different areas here. This is work that was essentially done by my soon to graduate PhD student Aman Goyal, who is on the call. Since we are from different communities, just wanted to give you who we are, So we basically do automated reasoning. The first modern conflict-driven clause learning set solver was developed in my group some time ago. We also did some work on fast symmetry detection. Most recently, we did automatic model checking for hardware. I'm going to talk about that a bit, and also a little bit on software. So we became aware of distributed protocols just a couple of years ago and became interested in kind of looking at that problem and why people think it's so difficult. Because we felt that we could probably solve it. So our background is hardware, finite hardware, and we took some inspiration from that to actually solve the problem of unbounded protocol model checking. So I'm gonna spend a little bit of time to talk about how we do inductive invariant generation for finite transition systems, and briefly mention how that has worked in hardware, then tell you about what we did in the past couple of years to extend that to unbounded protocol model checking, using the regularity in these protocols, in particular, their symmetry and temporal regularity. Then talk about the hierarchical structure of some complex protocols like Paxos, and then end by showing you how we actually did prove Paxos automatically. So if some of this is known, just somebody holler and I can speed this up. But this is just a quick overview of what model checking is. So you begin with something like a software program, hardware program, a finite protocol specification, something finite, and you pass it, so you model it as a finite transition system, state transition system. You pass it on as a transition relation T on state variables X and their next value, next state, X prime. We also specify an initial state, predicate I, and a safety property P. So this is the input now that goes into the, so this is the modeling step. We send that into the model checker, which will either say that, okay, the property holds under all possible execution scenarios, or it will say it fails, and here is a counterexample trace that shows you how it fails. And in some cases, it just may not give you an answer. It might not finish. So for this community, I think you understand what an inductive invariant is, and the question is, how do we find one? And one inductive invariant is basically the reachable set. If you can compute the reachable set and you can prove that the initial state satisfies the invariant, satisfies the property, and that the reachable set satisfies the property, then we know that P holds, and R would be the smallest inductive invariant. If the property doesn't hold, we know that, and we do these checks by doing SAT calls. So to show that the property holds, we need to basically say is R and not P on SAT, for example. Now, in case the property does not hold, we would end up getting R and not P is SAT, which means we have a counter example that shows we can reach an unsafe state from the initial state. P fails. The problem, of course, is that finding R in general is intractable. So this is not going to work. So instead, we try to do it by finding a strengthening assertion. We ask is R to check that R actually implies P, which in case it does, we ask if the query P and the transition relation and not P prime is SAT. If it is SAT, we know that P may be invariant, but it's not inductive. Okay, we can exit P and reach a unsafe state. So what we need in that case is find some assertion A such that R implies both A and P, and that both A and P are closed under the transition relation. So we want to show that A and P and the transition relation implies that I stay in A and P after the transition. So we get an unsat result from our query. Okay. So the question is now, we have to find this A and P is our inductive invariant that proves that the property actually does hold. The question is, how do we find A? And the thing that happened about a dozen years ago now is this incremental induction algorithm referred to as IC3 or PDR, which I'm just going to sketch for you just to show you what it actually kind of consists of. You instead of actually computing exact reachability, you do approximate reachability. So let's begin by giving some definitions over here. Okay, so the set of states reached in one step from the initial state, I'm going to call R1. And what I can reach in 2 steps is R2, and so on and so forth. Okay, and as I said, computing these to converge them to the complete reachable set would be intractable. So what I3 does is it says, let's compute an overapproximation of these reachability frontiers. Yes, and so the reachability frontiers are essentially contained within each other, starting with I and ending with the full reachable set. So what we're going to do instead is compute overapproximations called frames. Frame 1 overapproximates R1, frame 2 overapproximates R2, and so on and so forth. Okay, such that the frames themselves are also contained within each other. Okay, so these frames are basically how the IC3 algorithm tries to determine if if there's a transition from the initial state that will actually reach a bad state or prove that none exists, and ends up with an invariant that is inductive, proving that the property holds. So the basic step in IC3 would go something like this. Suppose that we have found a trace beginning in some state S in frame I+1 that has a path all the way to a bad state, this thing that is in red, and that's called a counterexample to induction. So we're in the middle of doing this, and we're maintaining these frames, and we want to say, okay, now I know that I can reach that bad state in so many steps, but is this reachable from the initial state? And we do that by asking, is it reachable from an earlier frame? So can I reach S from frame Fi? I do that by issuing the query, starting in Fi and taking a step, can I reach S? If the answer is no, then I know that I need to eliminate this counterexample, or at least the continuation of this counterexample from that state S. And we do this by essentially blocking S in frame I+1, meaning that I create a clause called not S that I augment to Fi+1. So the entire process inside this incremental induction procedure is over approximating what's reachable and then refining them based on determining if a partial counterexample to induction can be extended all the way to the initial state. Okay, so this was very quick and very brief, review of what IC3, the algorithm is. Is any question about that?
Can I ask a question?
You may, yes.
What if it's SAT? What if what if S can be reached from Fi?
Okay, then we go back and find another answer in Fi that we then have to check against something from Fi-1. So if the property actually does not hold, this could go all the way back to the initial state, and then we say the property doesn't hold.
So in the worst case, we might have to go back a few frames and try to tighten the previous frames also.
Right. So the process basically is an attempt to it's mostly backward reachability. You start from saying, can I reach a bad state in one step from my current frame? And the current frame is usually initialized to all safe states. And usually that is true. And so you try to eliminate to try to trace it back. In the process, in the middle of this, computation, try to block, all backward, impossible backward steps for it, and refining the frames as you go along. So it's basically kind of like a counterexample guided abstraction refinement procedure where you're doing queries to determine if you can go back in reachability and reach an initial state, but you don't have to go all the way back all the time. You can actually refine the frames kind of in the middle.
Thank you.
Can you say again how you create a new frame?
I'm sorry?
Can you say again how you create a new frame?
Yes, if we can eliminate, a counterexample to induction by having after having 3 frames, then we add a new frame, right? Which is kind of the most approximate frame, which is all the states that are safe, and repeat the process. But you understand that as we're doing this, we have already refined many, many other frames before it. And so in general, this procedure will converge very quickly, and it doesn't have to have the depth of the transition relation. It doesn't have to actually end up with as many frames as the depth. I'm really doing a very, very brief description of this. It's really a very clever procedure, and I encourage you guys to, if you have not looked at it, to take a look at it, because it's quite remarkable how it has pushed model checking to the point where we can do really huge problems with it. Okay, so we were doing this for hardware verification, which is finite state, and we do other things such as abstraction to remove states that don't matter and so on and so forth. This is just a braggy slide that shows that we won the hardware model checking competition last year by a wide margin, basically, because of using IC3 as well as what we call equality abstraction on data. So when we have very large state spaces that consist of data state, 64-bit integers and so on and so forth, we basically abstract those data states into an equality comparison between the various data variables without actually doing low-level bit manipulation on them. So this is where we are. So we have this, we're happy with it, and now we know, there is this other problem called distributed protocols, and it's infinite state. So can we look at that? And is there something that we can do to solve it? Okay. And we were novices, so we started reading the literature, and a lot of the literature on model checking of distributed systems, or so-called parameterized systems, hinted at the fact that they can be proved somehow by analyzing small finite instances and then generalizing to arbitrary sizes. A lot of it was kind of theoretical stuff. There is not much kind of in terms of implementing anything. And so we looked and we found lots and lots of so-called cutoff references, that you can just do a system of 3 processes or 5 processes and so on. I think for this crowd here, this is probably more relevant. This is from the TLA plus group, where somebody was asking about a set that has 1,000 elements and they wanted to simulate it. And I think Leslie said, well, if it's correct for 3 elements, it should, and not, it is rare to be correct for 3 elements and not for a set of 1,000. The intuition is that there is some regularity about these distributed systems, that you should make them easily verifiable by analyzing a small instance of them, okay? But we wanted to take this intuition and turn it into an algorithmic procedure for generating inductive invariants. I'm going to use this example. This is in TLA Plus that shows how we do this, okay? So this is, I think, was a toy consensus that was written by Ken Macmillan I think in the Ivy language, but this is kind of a version of it in TLA Plus. So we've got our domain constants here. We got the variables, which are the state variables. We got the assumption about quorums being subsets that have intersections. Then we have the actual actions, which is casting a vote and deciding. And these actions use quantified definitions, did not vote and chosen at. And then we have our initial state, the transition relation, and P. So we have essentially, in this example, domain constants that represent essentially unordered and indistinguishable objects, okay? And each domain constant is essentially symmetric, regardless of how many elements it has. And we also have the empty theory here. We don't have arithmetic. We just have basically the empty quantified first order logic theory with no arithmetic. We can have sequencing or order, but no arithmetic. So I'm going to use this template here to indicate the size of the problem that we're going to solve. So toy consensus on node quorum value, the arguments here are going to be the sizes. So if I have 3 nodes, I'm going to label N1, N2, N3, just arbitrary names. Then I332 would be the initial state on an instance that had 3 nodes, 3 quorums, and 2 values, and so on and so forth. So it's not important to dwell on this right now, but just understand that we're going to be talking about finite instances and figuring out how we're going to generalize from finite instances. Okay. Let me skip this here. Since we are hardware people, we kind of like to look at hardware diagrams. So the action of casting a vote, ends up really being like a small circuit like this. They did not vote, which is a definition variable, is actually just like a NOR gate on, node 1 voted for value 1, node 1 voted for value 2, or node 1 voted for value 3. It did not vote for any value, basically. So that's that. And then we have the state variable, which is node 1 voted. That happens if it had a cast vote instruction and it did not vote, then it would vote. Otherwise, it would just retain its value. So we have a multiplexer over here that says, okay, the vote is not updated if it has not voted. So we can see here that did not vote predicate there is essentially like a temporary variable or an auxiliary variable that is in our circuit. We call them wires in hardware. Okay. So this would be casting vote vote for value 2. I think I have a typo on this one here. Node 1 value 1. Node 1 value 2, I'm sorry, node value 3. Oh, no, that's fine. So this is these are all the possible ways that node 1 can vote for value 1, value 2, or value 3. So it either did not vote, it must not have voted for any of them, but then it would have voted for either V1 or V2 or V3, as shown by the command here, which is the action that it has to take. Decide is another circuit. Okay, again, I don't want to dwell too much on this. I'm just giving you a sense of how we view this. We view it structurally as a circuit, especially when it's finite. And interestingly, over here, there is there is a quorum that exists such that every member of the quorum has voted for a value. Okay, and finally, when we put everything together, we got the action for casting a vote, the actions for deciding, and then this last part is the property. Okay, so we want to show that in this circuit, P is always true. It's not violated under all possible executions from a specified initial state. Now, when we tried this initially with our hardware model checker, it worked, but it did not really scale very well, and it produced a very large invariant. And so we examined why that was, and we found it's because there is so much structure and symmetry in the protocol. So can we use that in order to speed up the reachability and to actually also reduce the size of the invariant? So suppose that we are in the middle of this reachability, and we learn that this state here, which is vote N2V1 and vote N2V2, can reach the bad state. So we are in frame I+1, and it has a path all the way to the bad state. And so this is the clause that we would learn if we notice that actually this state is not reachable from the earlier frame. And we notice that this could actually have been a different state that is equivalent to S. In particular, since all the nodes are indistinguishable, and I have 3 nodes over here, there are 6 permutations of these nodes, swaps and rotations and so on. So any of them could have been a possible answer to the queries that we sent to the stat solver. So rather than have the stat solver kind of enumeratively kind of generate them and we eliminate them one by one, what if we just invoke the symmetry and say, this S here can actually, or the negation, its phi, can be permuted, and we get these additional 5 permutations of the clause. 3 of them are essentially the same as something that we've seen before because of commutativity of AND. So we get 3 different clauses from the one that the solver gave us. We get vote N1V1, vote N1V2, and vote N3V1, vote N3V2. So we take each one of them, and now we permute the values. And here I'm going to use 3 values. So if I permute the values here, again, I would get different clauses. Some of them are redundant and can be removed. Okay, and end up with 9 clauses that represent the orbit of the clause that we started with. So phi is the clause it started with, and if you do all of this permutation stuff, you get 8 equivalents to it. So there's an orbit of that clause that is 9 clauses that are distinct, but they're all symmetric. And so what these do is, if you look at S as being the cube, that is the negation of the clause that is not reachable from Fi, these other clauses could have been solved, could have been found by the solver, but we're finding them by symmetry. And they share with S the fact that they can reach frame I+1, but they cannot be reached from frame Fi. Okay, so we can remove them all together in one fell swoop like that. That's called symmetry boosting. Okay. Not only that, but we can take these 9 clauses and express them compactly as a quantified clause. And this is done algorithmically, and in this case, it's kind of obvious to see how that works. We say for all nodes, for all values V1 and V2, if the values are distinct, then you cannot have vote and V1 and vote V2. Okay, which you can rewrite as for all n, for all V1, V2. If n voted for V1 and voted for V2, then V1 must be equal to V2. Okay, this is done automatically. And if you just want to convince yourself that this quantified formula is actually representing the same 9 clauses, we can instantiate this for all 3 values of nodes and all combinations of V1 and V2. And you can see that it survives to represent essentially it's an exact compact representation of the closed orbit. So the closed orbit is explicit. This is an implicit quantified representation of it. Here's another example just to give an idea of the generality of this. So this clause here has quorums in it. And in fact, for a 3-node, 3-quorum instance, it has all 3 quorums, the quorum that includes 1, 2, 1, 3, and 2, 3. And without getting into the detail, the inference from that is that we can infer an exists on the quorums with this clause that represents the orbit of that clause. And if you substitute the definition of what chosen at is, then you get this alternation of for all value exists a quorum for all nodes, right? So what we're doing here is we're letting the structure of the protocol dictate the kind of inference on the quantified clauses that will end up being in its inductive invariant. We are not searching for these forms. They drop out from this kind of analysis. Okay. Now the question is, what is the appropriate domain size that we can use, the finite domain size? So if we start with 3 nodes, 3 quorums, and 3 values, and we run this through our solver now, it will produce the following. The first one here is the actual property, that if you decide on V1 and V2, then they must be the same. And these are the strengthening assertions that it produced, okay? This is automatic. This is the one that I just showed you, and this is the other one that I showed you also, but without the detail of how we got it, okay? And we could say, oh, is that enough? Now, remember that these domains now are finite domains, and we want to go to a infinite domain, unbounded domain. So can we just drop the domain sizes here, the finite, and just say, then it's true for unbounded? And the answer is not so fast, because I could have started with 3 nodes, 3 quorums, and 2 values, and I would get the following from my solver. The second assertion here is different from the one that I got with 3 values. And you'd say, why is that? Well, because the algorithm for inferring these things looks at the size of the instance that you're giving it and produces something that is correct for that size. But it may not be correct for all sizes. So we need to figure out what would be the appropriate size to stop doing this, right? So one way to think about it is now we're doing multidimensional induction on size of the domains. So suppose here that I'm showing here the space of node and value sizes, because quorum sizes have to follow domain sizes, have to follow node sizes. They cannot be arbitrary. And so when I specify how many nodes we have, we know how many quorums we should have. And here we're showing an instance of 3 domains and 2 values, and we got the invariant for it. So N332 on 332 is the invariant we got by analyzing an instance of 2 or 3 nodes and 2 values. And now we check to see if I go to 4 nodes with this formula, is it still inductive? 4 nodes, 4 quorums, and 2 values. And it turns out here that it is inductive. But if I increase only the values, keep the nodes and the quorums the same, I found that it's not inductive. So that formula, the one that I showed you on the bottom last slide, does not generalize to a larger size. This is an indication that we have not converged, and we need to go back to a size that is 1 more on values. And now we create a new formula, N333 on 333. And we can then check, does it apply to more nodes? Yes. Does it apply to more values? Yes. And we conclude that this must then generalize to any size. So we dropped the actual finite size, and now we've got our final inductive invariant for the protocol. Okay. So this is how we find it. Now, for totally ordered sets, we have to
Just
do
a question.
something. Yes.
So is there any guarantees that it generalizes if you can go in those directions, or is it just a heuristic?
So empirically, this works in every case that we tried, and we're currently working on proving that it does actually work in general. Like it, so the invariants that we come up with are not in decidable fragment to first order logic, but we believe that we can prove convergence finitely on these things. We're working on that right now.
Cool, thanks.
Okay. So for totally ordered sorts, we need to do something more, okay? So why can we actually infer quantifiers on totally ordered sorts? Because that's an infinite sort now that is ordered. And the answer is because there's got to be some kind of temporal regularity that says we only need like a finite number of totally ordered quantified variables to express the invariant. So we came up with something called range boosting of a totally ordered sort. I'm going to illustrate it here with a little graphic. Okay, so suppose that we have now the same situation we had before, where now S here involves a totally ordered sort. So we can do the same thing we did with the symmetric sorts and say, oh, it's got this many other variants of it that are produced by permuting the constants of the sort in the clause. But then these three violate ordering. When you have two constants in a clause and one constant is representing, let's say, integer 2 and the other one integer 5, I cannot just randomly reverse the orders over here. So we need to keep the range or the ranges ordered. And so I can add a constraint before I do the actual refinement of the frame to remove these things, okay? So S3, 4, and 6 violate the ordering constraints, so they have to be removed. Secondly, of the remaining ones, not all of them are going to be like S. Some of them, like S2 and S1 and S8, can go to frame I plus 1 like S, but S5 and S7 do not go to frame I plus 1. So they are not similar to S. Okay, we're trying to find something that is equivalent to S so that we can collect them together and build a quantifier on them. So these cannot reach Fi plus 2. This requires us to make a query to the set solver, unlike with the symmetric stuff, which we didn't have to do. So these go out. And then finally, of the remaining ones, we find that S2 is reachable from an earlier frame. So it cannot be eliminated. So again, that requires a set query to determine that S2 has to go away. And then we remove that. And then the remaining ones now are equivalent to S, and I can then refine the frame with them, okay? So it's a bit more work when we have totally ordered set, but it's the same procedure basically of removing a collection of states rather than just single states. So I'm going to show you a quick evaluation of this. This all happened.
Can I ask a question?
Yeah.
This symmetry, as well as the totally ordered property, are these properties of the protocol that the language specification guarantees, or is this something that you are hoping for, but you may not be sure?
We don't hope for anything. We don't pray. These are in the spec, right? So when the TLA plus says constants, this, that, and that, it's implicit in that these are completely symmetric. If they're not symmetric, then this won't work. So we don't need an additional annotation for that. For totally ordered,
what do you mean this will not work? When you say this will not work, it means that you will fail to find an invariant, or something will be wrong?
The procedure is not applicable if you give me something that is not symmetric. So if you
it will still compute something, right? I mean,
no, we don't compute something. We just do not do it. Okay. So there is a basic assumption, which is the sorts on which protocols are based are either going to be symmetric sorts or totally ordered sorts, or maybe there is some partially ordered sorts or something. There is something that is implicit in how you define your replicas, if you will. In the previous talk, we heard about replicas. These things are indistinguishable, and so there is no way for the protocol to work if you assume that one of them is somehow special. If it's special, then we have to do something different for it.
Okay, thank you.
Maybe it's special and the rest of them are symmetric, right? But there is, right now, in all of the protocols that we looked at, everything is symmetric. All the acceptors are symmetric, all the values are symmetric, and so there is no additional annotation that is needed, at least in what we've seen so far. So, a lot has happened in the last 3-4 years. UPDR was an extension of IC3 to make it apply to unbounded SMT solving. And it was used recently to kind of check to see if it can find inductive invariants for various protocols. We have 40 of them over here that I'm going to show you in a minute. And it manages to solve about 17 of them, all requiring universal quantification. We did I4, which was our hardware verifier applied to protocols. And that was kind of our, let's just try this thing out and see if it works. And it works, but not all that well, again, because it's totally oblivious to the structure of the protocol, the symmetry of the sorts, the total order, and so on and so forth. Then additional work came from other groups with different ways of trying to find the inductive invariants. FOLIC3 solved 24 of those. This AI that's very recent, like a few months ago, solved 24. Swiss solved 23, quite fast. And then IC3PO. So IC3PO basically solved all of them except one, on purpose, because we have to show that we cannot do everything, right? So, but it validated empirically what we are trying to do and to prove kind of that the procedure is applicable in general to the kinds of protocols that have these attributes to them. Now, these 40 protocols, 10 of them had total order in them, and the IC3PO invariant that we produced, the shaded areas imply that they needed exists in the invariant. And this here says the shaded areas that they needed definitions in the invariant, and that the invariant had cycles between the quantifier alternation cycles. So some of them are totally undecidable if you want to do unbounded quantified reasoning. You cannot do it with SMT solvers. And this is how they distribute the results in terms of what each of the other solvers have done. Red means they didn't finish, or they had an error or something like that. So to us, this is kind of very interesting that we are able, coming out of left field and showing that there is a way, because we're problem solvers, there is a way to actually handle this kind of complex design space, the protocol design space. We're not experts in it, and there are other issues that might be there. But I think this is a good initial step to try and see, is there a way that we can automate the production of inductive invariants for this space? The inductive invariants that we produce are also quite comparable to the ones that are written by human beings, as you can see from this, sometimes even much better. And I'm going to end now by showing you how we did Paxos using hierarchical strengthening. So we started with an instance of Paxos that has 2 values, 3 acceptors, 3 quorums, and 4 ballots. And we tried to do this by just taking Paxos in that finite instance and just trying IC3PO on it like that. And it failed. It didn't work. It was too detailed, right? So we said, okay, there is another version of, and it has 147 state bits. So it's a large state space, but way smaller than the 60,000 and even, several 100,000 state bits in hardware. So what's going on with these protocols? Well, their state spaces are very dense. The out degree of every state is very large and grows with the size. But we know that there is an abstract version of this called voting that has only 2 to the 30th states. And so when we did that, and we got some assertions coming out of it, we thought, okay, maybe we can apply those to Paxos and see if it works. That also failed. That means the distance between these 2 abstraction levels is too high. So we came up with intermediate abstraction levels called simple Paxos. And now we can take the assertions coming from voting, applying them to the simple Paxos verification, and that finishes, and we get a few more assertions from that. Then we take those and to a lower level abstraction, and that produces some more assertions, and then those, and we get to prove Paxos in this fashion. Okay, so this is the hierarchical strengthening. It's basically repeating IC3PO by starting from a high level and then producing assertions for simpler and I'm sorry, more refined versions of the protocol until we get to the bottom. So I'm running out of time, I see here. So this is, for example, these are the two assertions that were produced from voting. These are automatically produced, okay? And then when you apply them to simple Paxos, you just map them over, okay? You get mapped over, and then automatically we get 3, 4, 5, 6 automatic. Then we take those and apply them to implicit and produces a few more, and then apply that and we get Paxos. Okay, so we get the exact same assertions that were manually written a few years ago for Paxos, automatically, assuming that for level hierarchy. So the question is this fully automated? And the answer is not quite, right? But what we can say is that formulas encoding the transition relation and invariance of unbounded protocols fall outside the conventional decidable fragments of FOL, which means that all of the work trying to kind of simplify them and get them into a decidable fragment is missing the point. You're trying to solve a different problem from the problem that the protocol is actually giving you. So we need to find a different way of actually finding the invariance. The regularity basically comes in to say finite reasoning and cutoffs is what is needed, okay? These things are so much easier than hardware because even though they're unbounded, they have built-in regularity in both space and time. And can abstraction be automated? So imagine if we did Paxos and it didn't converge. We have a lot of information about why it's not converging. Maybe there is a detail in there that is causing a lot of learning that is totally useless. And we're thinking about, is there a way to kind of abstract that away? And so to get the abstractions automatically. This is still far-fetched, you know, out there, but we might be able to actually learn from, you know, we do a timeout on a run and then figure out it's learning all of the stuff about this particular state variable. Maybe that state variable needs to be abstracted and maybe do that automatically. And there are other features. As I said, we're novices in protocols. You know, I heard about cardinality constraints. I heard about other things. So this is just first steps. What I hope from having you guys listen to this is, oh, this seems somewhat interesting. Can we pursue it together? Okay. Is there something that we can do together? We learn from you about protocols, and maybe you learn a little bit from us about how to do automated reasoning. And with that, I will stop.
Thank you very much. Very interesting talk. So we're running a bit late, so maybe we have time for just one quick question, but note that after the next talk, we have a discussion session scheduled where we can ask more questions.
Okay.
So any question?
I'll have a quick one because it's on the last slide. So at the end of this procedure, you still need to do a check in the unbounded domain, right?
So, no, we don't.
No.
Right now,
okay.
the reason we're doing it, right? First of all, for some cases we can't even do it because the invariants are not in a decidable fragment. But we are 99% convinced that our finite convergence is correct. We just need to prove it, right? So
okay, so not taking away from this approach, because I think it's amazing, but the current approach is not complete. Like it's not a proof for the unbounded case of the protocol.
Let me answer it this way. I'm not a computer scientist, but the fact that we got the exact same Paxos invariants, right, that were proved somehow by hand, right, suggests that the process is correct. Something is correct about it. It is, if you want to be technical about it, we don't have that proof that says that the finite convergence, is always true in all cases. Correct. But we have, as I'm saying, 99% kind of confidence that it's just a matter of time to show that that convergence will always be possible. Okay, and that's because, think about it this way: we're converging the strengthening assertions we're producing, and after a while, you're not going to see any new behaviors. This
Yeah,
observation
no,
has been found by others.
I would share the same intuition, and I would agree. But it's an intuition. But yeah.
So, I mean, if somebody on your side, guys, can actually help us complete the proof for that, I'd be more than willing to cooperate. But yes, we have some ideas of how to go about proving it, but it's not going to be a proof in the sense of, we want to prove that the actual assertions, converge. As we increase the size, we saw that induction process I was showing you, that after a while, you're not going to get any new assertions coming out as you keep increasing the size. That's how we're going about the proof.
Got it. Makes sense. Thank you.
All right.
Okay, thank you very much.
All right.
Let's switch to the next speaker, who is Rupcha Samantha from Purdue, who is going to talk about verifying unbounded distributed systems using bounded verification.
Thanks. I need to be able to share my screen.
Yes, just a second. Find you in the list. Okay, it should work now.
Okay, do you see my slides?
Yes.
Okay, perfect. So thank you again for the invitation and the opportunity to speak here. Lots of very relevant, interesting talks, and I'm actually so glad I'm going right after Karim, because that talk leads in very nicely to our work. Okay, but let me start at the beginning. So once upon a time, long ago, here is what happened. I want to verify distributed systems.
I really am too old for this.
Okay, please hear me out. Look, most distributed applications are built on top of some common distributed services, right? Such as data stores, logs, caches, queues, locks, and so on. And
so,
well, there is a pattern. All of these services typically rely on some notion of distributed agreement to perform their higher level functions. See, processes need to agree on a leader or the members of a group or owners of locks. I mean, think of Chubby, the Chubby lock service, or Redis Raft, or Apache Zookeeper's key value store, or even Cassandra distributed database. I mean, they are all based on distributed agreement. They are distributed agreement-based systems because they are built on top of agreement protocols like the Paxos and Raft consensus algorithms and the Zookeeper atomic broadcast protocol. See?
But you do realize that all these protocols have already been verified, right?
Well, that's exactly my point. So in order to verify the services that are built on top of these verified protocols.
You mean you're going to use modular verification?
Yes. So now that we have verified these agreement protocols, let's replace them with abstractions.
So if your programs are now simpler with abstractions, can you do the verification fully automatically, maybe model checking?
That's still a problem, unfortunately, because my system's still unbounded.
They're unbounded in terms of processes, variable domains, channel delays.
Yeah, that's right. But I think I can find decidable fragments.
But are these going to be scalable?
Well, I think I can make them scalable. I'll reduce my systems to a small bounded one using cutoffs, just like the previous speaker said.
Well, how about being usable by programmers?
Okay, I can design a simple modeling language that's accessible to programmers.
Oh, a modeling language, so they're not going to be executable.
Well, eventually we hope to get there, but don't you want to know how I can do all this?
All right, okay.
All right, so in our admittedly ambitious project Discovery, we seek to develop modular, scalable, fully automated and usable verification approaches for distributed systems that mimic their modular design. To enable modularity, we advocate an approach that is based on assuming that the underlying core protocols are verified separately and then encapsulating their complexities within cleanly defined abstractions. So while these protocol abstractions can yield distributed systems that are definitely simpler than their original monolithic counterparts, these are still too complex to enable scalable, fully automated verification, right? In fact, they are bounded along multiple dimensions, as we just saw. So the key technical question that we address in Discovery is, can we reduce the verification of interesting classes of such unbounded systems to the verification of small bounded systems? And then because Mr. Grumpy wanted things to be usable as well, we are developing modeling frameworks across multiple layers of abstraction, driven by insightful feedback and program synthesis approaches that can be readily used by system designers and hopefully eventually programmers. So this is joint work with my students, Noor Jafar, who was just grumpy right now, Chris Wagner, who's also on the call, Swan Jacobs, who is one of the organizers of FRIDA, and Milind Kulkarni. Swan is from CISPA, as most of you know, and the rest of us are at Purdue. So let me actually present to you an instantiation of our Discovery project that is going to appear in UPSLA 2021, just in a couple of weeks, which focuses on parametrized verification and modeling for distributed systems that are built on top of agreement protocols. Okay, so the core protocols that we are considering are agreement protocols like consensus and leader election. So for Quicksilver, we have three main, let me take you through three main contributions. We have a modeling language, Mercury, which has inbuilt primitives to abstract agreement protocols. We have decidability and cutoff results for parametrized verification. And then we have a nice tool that's also called Quicksilver that we have evaluated on a bunch of interesting distributed services, such as the ones shown on the slide, like distributed data store, distributed log, there's a robot flocking problem we have dealt with, and so on and so forth. Okay, there are many more. So let me begin with our modeling language Mercury and the two agreement primitives it supports. So the first primitive is called partition. Okay, and like its name might suggest, it allows a set of participants to divide themselves into two groups, winners and losers, say. Okay, now each partition agreement has primitive has an identifier. Okay, that identifies that particular instance of the primitive, and it takes two parameters: the set of participants and a cardinality, the desired number of winners, okay, or leaders. So upon termination of agreement, the winning and losing processes go to their respective locations and proceed with their respective tasks. Okay, so this is our primitive. And why is this interesting? Well, because it can capture agreement protocols such as leader election. Now let's move on to our second agreement primitive, which is called consensus. And as you might imagine, this primitive essentially allows its participants to agree on a set of values. So this primitive also has an identifier, and it takes three parameters this time: the set of participants, the number of values to be decided, and then a variable which could be optional that a process uses to propose a certain value, okay, for consensus. So I'm leading on to why this is interesting. Well, because you can model consensus protocols. So you might think that these primitives just model leader election and abstract consensus. But in reality, these can actually model multiple different kinds of protocols as well, including K-consensus. In fact, it can model protocols such as multi-paxos, Raft, and so on. So these are our agreement primitives, and let's now see how one might model or design an interesting distributed system such as a distributed store using these agreement primitives. Okay, so let's say we want to model a distributed store where multiple processes consistently replicate and update some stored data in response to client requests. Okay, now the clients may request various operations on the stored data, including read and write, read and update, right? Now, to ensure data consistency across the replicas, suppose me as the designer decide to use distributed agreement protocols, right? In particular, to do this efficiently, I decide to use a leader election protocol to first elect a leader who is going to handle the client requests. Okay, there's a single point of contact for the client. And then I decide that the leader can coordinate with the replicas to agree on which client request to execute. So using some notion of consensus, and once the command is executed, the leader can confirm, can send an acknowledgement to the client. Okay. So let's see now how one would model this system in Mercury using the agreement primitives we just discussed. So here is the entire process definition in Mercury. You don't really have to go through all of it. I'll highlight the things you need to notice. Okay, so in general, a Mercury process consists of some declarations of local variables and communication actions. And then it has a sequence of locations, each with its own event handlers, okay, where events can be broadcasts and rendezvous, or they can be agreement primitives. So here, first in the leader location, as you see, the leader can serve, at the initial location, you first do leader election, right? We want to elect a leader while the other processes act as replicas. So we do leader election, and you can see that we have used our partition primitive to model this. Then in the next location, which is the leader location, we essentially process the client request based on the specific request that the client provides. Okay, so this client request is obtained in this do command message, which can take different values according to the types of the requests. So this is essentially stored in the payload. And depending on the value, the leader might, for instance, decide to, if the client just requests a read from the data store, the leader might just process that client request, or it might move on to another location where the command can be executed. Okay, for instance, if the command needs to be replicated, it can move to a location to coordinate with the replicas on the command to be executed, right? So upon agreement, processes can then proceed to execute that command, and then the leader confirms the operation to the client. And finally, if the leader crashes, we allow modeling process failures. If the leader crashes, we want to allow the replicas to elect a new leader. Okay, so as I already said, we use the partition primitive to model leader election. And notice that we use the consensus primitive to model agreeing on the command to execute. So even though we are not going to look at this process definition in detail, I want you to notice that the design is very modular, right? All right.
May I ask a quick question?
Sure.
So if you have a leader, why do you need consensus? You could just get the value from the leader.
Well, this is a distributed store. So the purpose of the distributed store is to replicate the data for improved safety, right? For improved tolerance. And so this, this is not a single process store.
Okay.
Does that answer your question?
Yeah, I'm not sure. Okay, maybe it's just continue.
Yeah, perhaps let's get back to this later. Okay. All right. So let's see how we define the semantics of such a Mercury process. Okay. Now, as most of you are going to be you're going to find this pretty easy to understand. The semantics is essentially modeled as a labeled state transition system, as shown here on the right. Okay. So execution starts in an initial state corresponding to the initial location, the candidate location, and an initial valuation of all the variables. Now, from this state, one can execute the partition primitive. And then depending on whether you win or lose the partition primitive, you move to a state corresponding to the leader location, or you move to a state corresponding to the replica location, right? And then from the leader state, one can perform a set of actions, as we saw before, based on the specific request received from the client. And so, these three possible actions are just shown here to a certain extent. Okay. So this is, I'm not defining this. This is fairly standard. So these are the process level semantics, and essentially the new ingredient here is our agreement primitive. Okay, so the labels corresponding to the agreement primitives. The other labels correspond to the specific event that a process processes. So if it's a send or a receive or a broadcast or a rendezvous action, and so on. So that's the process level semantics. Now, what about the program semantics? Okay, what is a Mercury program? So a Mercury program, like in the previous talk, is also a parametrized system consisting of multiple copies of the same process definition. Okay, so n here is the parameter, it's the number of processes, and p1 through p sub n here are identical processes. Okay, so this is symmetric. Now the semantics of M of n is essentially, I mean, it is a global transition system. Okay, and it is essentially composed of two things. Most of it is a standard product like you would construct given the local transition systems for the semantics of each process. But we also need to figure out how to incorporate the semantics, some special semantics corresponding to the agreement primitives, right? So again, this is an abstract view of what we do. So remember that these agreement primitives are meant to abstract verified agreement protocols. Okay, so we can't just have a syntactic representation, a primitive of the protocol. We need to associate a specification, a semantics with the primitive that capture the fact that the agreement protocol has been verified. Okay, so the global semantics that we associate with agreement primitives are essentially stated, encoded as a precondition postcondition pair, which can be stated informally as essentially a precondition that captures consistency of the participants on agreeing with whom to invoke agreement. Okay, consistency about the participants, the set of participants. And this post condition, which essentially captures the fact that upon termination of agreement, all participants agree on the winners or the values, depending on whether it's partition or consensus. Okay, so we are able to augment this primitive with this precondition and post condition because we have assumed that the underlying protocol has been verified. Okay, so to make this more precise, we show that our agreement abstractions are sound. What does this mean? So if you start with an agreement protocol that is verified, in particular that satisfies the standard agreement validity termination criteria, then the abstraction specified by our agreement primitives and their semantics is sound. Okay, so it means that the protocol also satisfies this precondition postcondition pair. So that is what we mean by our abstractions are being sound. Any questions before I move on to the next part? All right, so that's our modeling language. Let's now talk about parameterized verification. This is a pretty high level talk because I want to put forth an idea rather than dive too deep into the specific technical results we have about decidability and cutoffs, because as you will see later, this approach is supposed to be a very general approach, okay, that is not tied to specific approaches for proving decidability or specific means of obtaining cutoffs. So let's just talk about this at a high level. Just to review, the parameterized model checking problem seeks to see if a distributed system composed of an arbitrary number of copies of a process satisfies a certain specification. Okay, in general, a temporal logic specification. Let's just call it phi for now. And this is a very well-known undecidable problem. So we show in our work that this particular problem for Mercury programs is decidable under certain conditions. Okay. In particular, we show that if a Mercury process is what we call phase compatible and the specification is what we call permissible, then this PMCP, this instance of parameterized model checking for Mercury programs becomes decidable. Okay. So what are phase compatible Mercury processes? Well, I can just give you an informal intuition. A Mercury system can be seen as essentially proceeding in phases where all processes are in some set of local states and then some global synchronizing action, okay, like an agreement protocol and so on, occurs, which moves the entire set of processes to the next phase, okay? And the phase compatibility conditions essentially ensure that the system's ability to move between these phases is independent of the number of processes. So that's what it ensures. And what about permissible safety specifications? Well, these are essentially safety specifications which forbid the reachability of any global state where some specific number, M or more processes are in some set of local states. Okay, so examples of such specifications include mutual exclusion and various process local safety properties. So for our distributed store, for instance, the safety property is that no global state with, you can have no global state with 2 or more leaders. Okay, every global state with 2 or more leaders is an error state. So how do we do this decidability? Again, I'm just going to give you some intuition. So this is also hierarchical, and we call this layered in the sense that Karim just mentioned earlier. Okay, it is very difficult to directly reason about the decidability of Mercury programs because they look like programs. Okay, so what we do is we actually rely on a previous result, okay, which showed that a certain computational model that we proposed in a paper in CAB last year called the Global Synchronization Protocols, which are a pretty abstract theoretical computational model for capturing distributed agreement systems, can be decidable under certain conditions. Okay, so we define these global synchronization protocols which can abstractly model agreement-based systems, and we extracted decidable fragment corresponding to it. Okay, and the decidability result essentially was based on well-structured transition systems, if you are interested. In this OOPSLA paper, what we did was we expanded the global synchronization protocols into a broader computation model called Mercury Core. And then we show that there is a simulation equivalence between programs in Mercury and between the abstract models of programs in Mercury Core. Okay, so essentially by moving through convenient layers of abstraction that enable us to reason about decidability, we can prove results at higher levels of abstraction and port them down to lower levels of abstraction. So this is where I just want to pause for a second and essentially talk about a general idea, right? Which is at the core of what we are trying to say. So apart from modularity, right? Exploiting the availability of verified agreement protocols. The key insight in our discovery project is that we really need to be able to operate at different levels of abstraction of models and modeling languages. Okay, it is not enough to just talk about abstract transition systems, and it is very difficult to do anything with implementations, actual implementations, executable implementations, unless in some very specific restricted cases, right? And you can get more and more automation as your system becomes more and more abstract, but then who builds these models? Okay, can programmers really write a higher level computational model that can perhaps be automatically model checked? So we need to really think about these two important criteria, right? About usability and provability, perhaps through automation. In the lower layers, we could rely more and more on deductive verification, which could be semi-automated, interactive. In the upper abstract layers, we could use parametrized model checking, or perhaps, as Karim was mentioning, some decidable fragments of first order logic, right? So you could use various decision procedures for the more abstract levels, but then we need to think in terms of this hierarchy, this layering of models in order to slowly move towards implementations. Okay, so that's sort of one of the takeaways I want you to remember from this talk. Let's get back to our cutoff, decidability and cutoff results. I just told you about the conditions under which this problem is decidable. Okay, the corresponding decision procedure is not scalable at all. So we rely on cutoffs. We want to rely on cutoffs for scalability, right? And a cutoff, as you know, is a certain specific number of processes, such that if the system is safe for any number, for the cutoff number of processes, then the system is safe for an unbounded number of processes, and vice versa. Okay, and these are nice because they allow you to reduce an unbounded, the verification problem of an unbounded system to the verification of a bounded system. Okay, so we, in addition to phase compatibility and permissibility, we identified another set of criteria on this model checking problem called cutoff amenability criteria, which enable us to derive small cutoffs. Okay, remember that our specification was of the form that you cannot have more than a certain number of processes, say M, in a global state. Well, these cutoff amenability conditions essentially identify criteria under which the minimum number of processes needed to reach such an M process error state is in fact M. Okay, now remember, this is a distributed system. Processes cannot always move on their own independently, because they might, for instance, a process that has to receive an action depends on another process to send. So there is some dependence on what an individual process can reach, and cutoff amenability essentially identifies conditions under which the required number of processes can freely reach the error state. Okay, so that's all I'm going to tell you about our decidability and cutoff conditions. And before I move on to the evaluation, I wanted to see if there are any questions. All right. So,
question maybe?
Yeah, sure.
So yeah, we're talking about parameterized but finite state processes, right?
That's right. That's right. Yeah. And I'll come back to that later. Good point.
Okay. Yeah. Thanks.
Okay. So we have implemented this in a Quicksilver tool built by Noor and Chris. And here is what the tool essentially does. Okay, it starts with a Mercury program and a permissible specification, and it does some pre-processing. Okay, and then it checks if this program, this process is actually phase compatible. Okay, if it isn't phase compatible, which means it does not fit into the decidable fragment of Mercury, then our tool gives some feedback. Okay, in the interest of usability, our tool attempts to give some feedback to the user, indicating how the user might fix their system in order to fit it into the decidable fragment. okay, or to at least eliminate the counterexample to phase compatibility. Now, let's say perhaps with some round of feedback, we do get a phase compatible system, or the user starts off with a phase compatible system. Then we check if is it cutoff amenable? Can it enable scalable verification? Because it's not enough for verification to be decidable, right? If it is not cutoff amenable, then again our tool does some best effort attempt to provide some feedback to the user. Now, I'm not going to claim that our feedback right now in the tool is where it should be. I think the feedback for phase compatibility is pretty good, but we are still working. There is a lot more work to do, right? These are first steps. And so if the process is now found to be cutoff amenable, by the way, these conditions, phase compatibility, cutoff amenability, they are all checked on the process local semantics. Okay, you do not have to work with the global semantics for these. This is critical. So if the process is cutoff amenable, then you compute the cutoff, you do the verification for the bounded system of size equal to the cutoff, and if it passes the verification, then you declare that the system is safe. Otherwise, you have a counter example, which is again fed back to the user, right? So that the user can change the system. So that's essentially the basic algorithm implemented in Quicksilver. And we have a variety of benchmarks that I mentioned before, including the distributed data store that I showed you earlier. There are also, there's a sensor network, distributed register, and so on. I'm not going to show you the exact numbers for all of these benchmarks. What I want you to emphasize that our modeling language can efficiently model complex distributed services, and it can efficiently verify these complex distributed services. So the Mercury models for all our benchmarks were within 100 lines of code. The cutoffs were all within 5 processes, and the total verification time was within 12 minutes. Okay, so this is fully automated, decidable verification of these distributed services, once you assume that their underlying protocols are abstracted. So to come back to the question earlier, I want to clarify, it's always important to point out what are the assumptions made in your work, right? So these are our current assumptions in Quicksilver. The communication model is synchronous, okay? So processes might do things asynchronously, but communication is synchronous. We allow for process failures, but we assume that the network is reliable, okay? There are no channel delays, there is no message loss, and so on. And the processes are finite state, okay? So this might seem like a heavy set of restrictions, and I would agree, except we needed to start somewhere in order to obtain decidability, right? Decidability is just not easy to extract, but we are currently working on essentially extending these same ideas to derive reductions to bounded systems along multiple dimensions, not just along processes, but along variable domains, along channel delays, and so on. Okay, we are trying to extend this idea of developing or deriving cutoffs, not just for number of processes, but for other kinds of unboundedness as well. So this is very much ongoing work. Discovery is ongoing work. So in Quicksilver, we have sound abstractions of agreement protocols, right? We have a modeling language that does this. We have scalable automated verification through decidability results and cutoff results. And we get usability through our modeling language, through the design of our modeling language, as well as through the incorporation of some notions of user feedback in the loop, right? So that's Quicksilver, and I just want to end again with a review of what our overall ambition is in this discovery project, right? We want to go beyond agreement protocols and look at other kinds of abstractions of core protocols as well. We want to try and do reductions to bounded systems along multiple dimensions. And we really want to try and develop modeling languages across multiple layers of abstraction and make the whole system usable through insightful user feedback, and program synthesis when applicable. So that's it. That's discovery. Thank you for your time.
Thank you very much. Very interesting talk. Let's take a few questions.
So question, so you mentioned using like the partition primitive to do a leader election. More generally, can I use it to do kind of reconfiguration of which nodes are going to be involved in subsequent consensus rounds? Is that right? Or
yes, yes.
Okay.
Yeah. That's how you can do multi-paxos.
Right. Okay.
I have a quick question. Are there any benchmarks or the tool available open source or openly available?
We are all, yes, we did pass the artifact evaluation for UPSLA, and it should be accessible. I don't have the link with me right now, but perhaps you can email Noor Jaber and he can send you the link.
Thank you.
Sure.
So I have a question.
Yes.
Could you give some intuition as to why the phases help obtain the decidability of the problem?
Okay. I'm going to give some intuition, but since there are a lot of my co-authors here, including Noor and Swan, I'll let them take over if they wish to. Okay. So phase compatibility is just a certain syntactic criteria at the level of a Mercury process that we obtained in order to map into the decidable fragment of the global synchronization protocols. Okay. So phase compatibility corresponds essentially to the well-behaved global synchronization protocols that enable decidability for that computational model. Okay. So, to understand the intuition, it is actually helpful perhaps to think across both of these computational models. Okay. So the global synchronization protocols essentially allow for global guards which state that processes can be in some set of local states. Okay, this is what is the abstraction for agreement in global synchronization protocols. And the reason it is decidable is because it enables, I mean, it enables that it is decidable for global synchronization protocols which move in step, okay, where all the processes are in some set of local states, they satisfy some global guard, then they all move to some other set of global states, and then they all move to some other set of global states. This movement is independent of the number of processes, okay? And this is what is lifted into phase compatibility for Mercury processes, where essentially you want to ensure that all processes in the system are in some set of local states, and they, independently of the number, they are able to move, they are able to globally synchronize into another phase. I don't know if that clarifies it, and I don't know if Swan or Noor want to add anything to it.
Yeah, it clarifies a little bit. Still remains a little abstract, but yeah, I should read the
so I think
it is very difficult to give anything more than an abstract intuition for this, unfortunately. If you look at our well-behavedness criteria or phase compatibility criteria, they are extremely ugly. I have to admit, okay? This is the reason why we have user feedback, because we cannot expect a user to magically fit their programs into our decidable fragments. These are not easy to enforce syntactic criteria for a user, okay? That's why, I mean, we have characterized the decidable fragment, okay? We know how to check for it out automatically, but we need to help a user in order to map their programs into these decidable fragments, okay? So all I'm trying to say is, unfortunately, the criteria are technically intricate, and there is very little high-level intuition that we can give beyond what we just said. But I'll let Noor and Swan add more.
I think like Rush just said, like by the end of the day, it really is to enable some sort of an equivalence with the decidable fragment in the GSP. But the way I like to think about these phases is that, so if you know that your system is in some subset of its local state space, and we want to make sure that if I have 4 processes or 5 or 10, or which of these states is currently occupied, that I can still perform an action, because otherwise, without that independence, we don't really get this nice notion of parametricity. In different sizes of the system, then you will have the system may get stuck in this phase or may leave the phase and so on. So to ensure that we're somewhat independent from the number of processes, which then makes it, which paves the way into decidability, is to ensure that regardless of where your processes are in this current phase, if they wish to leave to a next phase, they can all synchronize and leave, and there is no, I think this is really how I would like to think about this. It's the movement between these phases is not dependent on which current system size you're in. And so you get this like whole parametric notion.
So if I understand correctly, you're kind of abstracting the system into this higher level phase transition system where in each phase is, I guess what matters is the set of local states that are covered instead of how many processes are in each local state. Is that accurate?
Yeah, I mean, these constraints are, yes, these global guards or phases essentially correspond to all processes, not a certain number or some, all processes being in some set of local states.
Okay. Thanks.
So I'm trying to get some intuition about this primitive. So for instance, if I have consensus, just consensus, what is n there if it's a primitive, right? Why do I need a cutoff larger than 1 if consensus is just a built-in primitive?
Wait, I'm not sure I understand, but we allow our consensus primitive to also model K consensus, right? So you could choose an arbitrary number of values, which is specified as part of the consensus instance. We are not just doing standard consensus where you pick one value.
But if I want to pick one value, what shall I do? What shall I do if I want one value? I'm like in blockchains, I need one value.
Yes, actually in blockchain, we thought about blockchains a lot, and Chris can actually talk more about that. We tried to see if we can actually apply this to blockchain systems, but there it seems like you automatically get consensus and there is really not much to verify. They were much simpler systems than what we need. Is that right, Chris, or would you like to add something?
I think what we ran into with blockchain systems is that their distributed nature is somewhat different from the systems we've been looking at. With a lot of blockchains, there are pockets of agreement among processes, but it's difficult to draw a line that at this point, all the processes that are participating in the chain will have reached the same conclusions, within a certain window. Basically, we might be able to assume there's agreement beyond a certain point far enough back, but we don't perform necessarily a single round of consensus the way that you would in something like Raft or Paxos.
Oh, you mean you don't always know whether all processes have decided, right? That's
right, for at least for a fully distributed blockchain. For something like a consortium chain, we have a slightly more centralized notion of consensus. We can model that a little bit better. But for something like a proof of work, if you were trying to model the consensus mechanism for Bitcoin, it doesn't match up quite as well to our primitive.
Yeah, I think go ahead.
I'm sorry, go ahead.
So I just wanted to add to the question about I think even if you're trying to do consensus where you're trying to agree on a specifically one value, just to get your processes sometimes in a state where they're ready to perform consensus, you might need additional processes in order to be in a state to even do consensus. So regardless of the cardinality, sometimes you might have leader election before that, or just normal broadcasts and so on, that you essentially need to have diverging processes. You need to have, say, 2 processes win an election for the rest of the system to do consensus. So technically, the cutoff then would be 3. So there are, I think what I'm trying to say is that there are other reasons that would make the cutoff grow. And I believe even if your whole system is consensus, is that like if you're trying to say, it depends really on your, depends on the kind of specifications you're trying to do. But imagine if I'm trying to check if you've actually reached consensus, then a counter example to that, even without knowing what the system look like, will at the very least need 2 processes, right? Because I need to have 2 processes and I need them to disagree. And that would be my kind of error state, if you will. So I think this is a long answer to, you could need other processes even if you're doing a consensus for cardinality of 1.
I was just curious about the middle layer, the scalable automated verification. So what kind of verification technology goes into that for verifying the small cutoff sizes? Like, is it using SAT SMT based model checking, BDD based, or explicit model checking?
It is SMT based model checking, right, Noor?
Also, so the current way we do finite.
We have changed the implementation also a couple of times, yeah.
The current implementation is that we are doing an explicit, like we just enumerate all the states, like a traditional model checking currently. But there is a way to, there is probably a way to switch that to some sort of an SMT, but so far it hasn't been a problem in terms of.
Okay, sorry. Maybe I need to, I thought our model checking was symbolic, but we can see that later.
Thanks.
I think I'm just mentioning, I'm just talking about Kinara, which is really a finite state model checker.
Okay, so thank you very much. I think we'll close the questions for this particular talk now, but we now have the discussion session where I'm going to split us into 2 breakout rooms, and we can discuss more about any of the talks that we've heard at FRIDA.
Thank you.
So let me create the breakout rooms.